Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillows, let your body settle into the softness beneath you, and know that for the next couple of hours, there's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom where the night has already fallen? A cozy corner where you're winding down from a long day? Wherever you are, you're welcome here. Tonight we're going to explore something that appeared in our solar system in the summer of 2019. Its name was 3I/ATLAS, and it was only the second interstellar object we'd ever detected passing through our cosmic neighbourhood. But unlike its predecessor, Oumuamua, this visitor left scientists with questions they're still contemplating today. Questions about its composition, its trajectory, its behaviour as it approached our sun. Questions that made some researchers wonder if what we were seeing was entirely natural. We'll discover what made this object so unusual, understand the evidence that puzzled astronomers, and contemplate what it might mean for our understanding of what travels through the space between stars. But don't worry, this isn't going to be a journey into conspiracy theories or wild speculation. Instead, we'll move slowly and carefully through the actual observations, the peer-reviewed research, and the thoughtful debates among scientists who study these rare visitors. By the end, I think you'll find not alarm or certainty, but something more valuable, a deeper appreciation for how much we still have to learn and how the universe continues to surprise us in the most fascinating ways. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in, let your shoulders drop away from your ears, take a slow breath, and let it out even more slowly. And let's begin our slow drift through the story of 3I/ATLAS, the interstellar visitor that didn't behave the way it should have. There's nowhere you need to be. Just listen and let the story unfold like starlight across the darkness. On the 14th of August 2019, an automated telescope system in Crimea captured something unusual. The Atlas Survey, which stands for Asteroid Terrestrial Impact Last Alert System, had been scanning the night sky as it did every clear evening, looking for objects that might pose a threat to Earth. But what appeared in the data that night wasn't heading toward us. It was passing through. The telescope is located at a facility that has been observing the heavens for decades, perched on a hillside where the air is clear and the light pollution minimal. That night, the system's cameras detected a faint point of light moving against the background stars. At first, there was nothing particularly remarkable about it. The software flagged it as a potential comet, something that happens dozens of times each year as these icy wanderers from the outer solar system make their long journeys around the sun. But when astronomers reviewed the trajectory over the following nights, they realised something extraordinary. This object wasn't following an elliptical orbit like the comets and asteroids native to our solar system. Its path was hyperbolic, meaning it had come from somewhere else entirely. It was moving too fast to be gravitationally bound to the sun. It was just passing through our neighbourhood, the second confirmed interstellar visitor in human history. They designated it 2I/Borisov initially, after Gennady Borisov, the amateur astronomer who operated the telescope that night. Later, as more observations refined its trajectory and the astronomical community confirmed its interstellar origin, it would also be catalogued as C/2019 Q4 and eventually referred to in scientific papers by the designation that would become most common, 3I/ATLAS, acknowledging both the discovery system and its place as an interstellar interloper. The discovery sent a wave of excitement through the astronomical community. 2 years earlier, in 2017, the first confirmed interstellar object, 1I/Oumuamua, had caused tremendous interest and debate. That object had been strange in many ways, tumbling through space with an unusual, elongated shape and accelerating slightly as it left the inner solar system in a manner that couldn't be fully explained by outgassing alone. Some researchers had even published papers suggesting it might be artificial, though most scientists remained sceptical of such claims. Now, with a second interstellar visitor, astronomers had a chance to study something from beyond our solar system with better preparation. Oumuamua had been detected as it was already leaving, giving researchers only a brief window to gather data. But 3I/ATLAS was discovered on its way in, providing months to prepare observations and gather information from every available telescope. The initial observations showed what appeared to be a comet. It had a fuzzy coma, that cloud of gas and dust that forms around a comet's nucleus as solar radiation causes ice to sublimate into space. It had a faint tail, stretched out behind it by the pressure of sunlight and the solar wind. In many ways, it looked exactly like what you would expect from a distant comet making its first pass through the inner solar system. And yet, as the weeks passed and more data accumulated, certain aspects of 3I/ATLAS began to seem unusual. Not dramatically so, not in ways that immediately suggested anything other than natural processes, but unusual enough that careful observers began taking note and comparing their measurements with what they expected to see. Let's explore what they found. To understand what made 3I/ATLAS special, it helps to understand what we mean when we say something is interstellar. Every object in our solar system, from the closest asteroids to the most distant comets in the Oort cloud, is gravitationally bound to the Sun. They follow elliptical orbits, returning again and again in predictable cycles that can last from a few years to millions of years. When astronomers track an object's movement across the sky night after night, they can calculate its orbit with increasing precision. They determine not just where it is now, but where it came from and where it's going. For objects bound to the Sun, this calculation produces an ellipse, that oval shape where the Sun sits at one of two focal points. The object swings close to the Sun at perihelion, then travels out to its most distant point at aphelion, before falling back inward again in an eternal dance. But occasionally, very occasionally, an object appears whose trajectory doesn't close. Instead of an ellipse, its path forms a hyperbola, an open curve that approaches the Sun once and then departs, never to return. The object is moving too fast, carrying too much kinetic energy, to be captured by the Sun's gravity. It came from somewhere else, and it's going somewhere else, and our solar system is just a brief stop along an unimaginably long journey. The orbital eccentricity tells us this mathematically. An ellipse has an eccentricity less than 1. A parabola, which would represent an object moving at exactly escape velocity, has an eccentricity of precisely 1, and a hyperbola, indicating an unbound trajectory, has an eccentricity greater than 1. When astronomers calculated the orbit of 3I/ATLAS, they found an eccentricity of approximately 3.3, not even close to bound, definitively interstellar. But where do interstellar objects come from? The space between stars isn't empty, though it's far emptier than anything we experience on Earth. In every cubic metre of interstellar space, there might be just a handful of atoms, mostly hydrogen. But there's also dust, and occasionally larger objects, rocks, ice, things that were ejected from other solar systems during the chaotic early periods of planetary formation. When planets form around a young star, the process is violent and messy. Massive objects migrate inward and outward, their gravity flinging smaller bodies in all directions. Some of these smaller bodies, unable to find stable orbits, achieve escape velocity and are cast out into interstellar space. They become wanderers, travelling through the galaxy for millions or billions of years, until perhaps by chance they pass through another star system. Our own solar system likely ejected countless objects during its formation 4.5 billion years ago. Jupiter, in particular, with its immense gravity, probably flung enormous numbers of comets and asteroids into interstellar space. And what we did, other solar systems did as well. The galaxy is filled with these orphaned objects, moving between the stars on journeys that dwarf any human timescale. Most of them we never see. Space is vast and these objects are small and dark. They reflect almost no light when they're far from any star. The only time we have a chance to detect them is when they happen to pass through the inner solar system close enough to the sun that they warm up and become visible, either by reflecting sunlight or, in the case of comets, by developing that characteristic coma and tail. Before 2017, we had theorised about interstellar objects but never confirmed one. Astronomers knew they had to exist. The mathematics and computer models of planetary formation made it clear that every star system should eject material. But actually catching one passing through required both luck and capable survey telescopes, scanning large portions of the sky regularly. Oumuamua changed that. Its detection proved that our telescopes had finally reached the sensitivity needed to spot these visitors, and it suggested that interstellar objects might pass through the inner solar system more frequently than we'd thought, perhaps one every year or two within the orbit of Jupiter, though most would go undetected. When 3I/ATLAS appeared just 2 years after Oumuamua, it seemed to confirm this new understanding. We were entering an era where detecting interstellar visitors would become routine, giving us windows into the planetary systems of other stars. Samples of material formed in stellar environments different from our own. Each visitor would be like a message in a bottle, carrying information about its place of origin, and what 3I/ATLAS seemed to carry was a puzzle that scientists are still working to understand. Before we examine what made 3I/ATLAS unusual, it helps to understand what a typical comet is and how it behaves. Comets are often called dirty snowballs, though that description doesn't quite capture their complexity. They're better thought of as frozen reserves of the early solar system, preserving materials from the time before the planets fully formed. A comet's nucleus is typically a few kilometres across, though sizes vary considerably. It's composed primarily of water ice, mixed with frozen carbon dioxide, methane, ammonia, and various other volatile compounds. Embedded throughout this ice are dust particles, rocky grains, and organic molecules, the carbon-based building blocks that make life possible. The whole mixture is frozen solid, a solid mass that can survive for billions of years in the cold of deep space. But when a comet's long elliptical orbit brings it closer to the Sun, everything changes. As the nucleus warms, the ices begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. This process starts when the comet is still quite far from the Sun, well beyond the orbit of Mars, as soon as the solar radiation provides enough energy to liberate the most volatile components. The gas carries dust particles with it as it streams away from the nucleus, creating the Coma, that fuzzy cloud that can grow to be larger than Jupiter, even though the nucleus itself might be only a few kilometres across. The Coma glows, partly by reflecting sunlight and partly through fluorescence, as ultraviolet light from the sun energizes the gas molecules, causing them to emit their own light at specific wavelengths. As the comet draws even closer to the Sun, the pressure of sunlight and the stream of charged particles known as the solar wind push the gas and dust outward, creating two distinct tails. The dust tail is broad and curved, following the comet's orbital path, composed of those rocky particles that reflect sunlight and give many comets their beautiful sweeping appearance. The ion tail, formed from the ionized gas, is straighter and narrower, always pointing directly away from the Sun. Pushed by the solar wind and sometimes glowing with a bluish light from the fluorescence of carbon monoxide and other molecules. This outgassing also affects the comet's motion in a subtle but measurable way. As gas jets away from the nucleus, it creates a small rocket effect, a thrust that can slightly alter the comet's trajectory. This non-gravitational acceleration is well documented and must be accounted for when predicting where a comet will be weeks or months in the future. The effect is small, but with precise measurements it's detectable and expected. Different comets outgaze at different rates depending on their composition. Some are more icy, producing large amounts of gas and dramatic tails. Others are more dusty, their ice locked within rocky material, making them less active. As a comet makes repeated passes close to the Sun, its most volatile ices gradually deplete. Each passage strips away another layer, and eventually, after many orbits, a comet can become dormant, its surface covered with a crust of non-volatile material that insulates whatever ice remains below. Scientists have become quite skilled at predicting how comets will behave based on their brightness, their distance from the Sun, and their composition as revealed through spectroscopy. They can estimate how much gas a comet should be producing, how large its coma should grow, how it should accelerate from outgassing. These predictions aren't perfect, because each comet is unique, but they're grounded in decades of observations and a solid physical understanding of how ice sublimates and gas escapes. When 3I/ATLAS appeared, astronomers naturally expected it to behave like other comets. It had a coma. It appeared to be outgassing. Its spectrum showed the signatures of the molecules expected from a comet, water and carbon compounds and other familiar features. In almost every way, it looked like a normal comet that happened to be on an interstellar trajectory, a visitor from another star system that was fundamentally similar to the comets born around our own Sun. But as the observations accumulated and researchers analysed the data more carefully, certain details didn't quite match expectations. The deviations were subtle, the kind of thing that might be easy to dismiss or attribute to measurement uncertainty. But they were persistent. And in science, persistent anomalies are worth paying attention to because they sometimes point towards something genuinely new in our understanding. One of the first unusual things about 3I/ATLAS that caught astronomers' attention was how bright it was relative to how much it should have been outgassing. When you observe a comet, you can measure two related but distinct things: its brightness and the rate at which it's producing gas and dust. For typical comets, these measurements correlate in predictable ways. A comet's brightness comes primarily from sunlight reflecting off the dust particles in the coma and tail. The more dust, the brighter the comet appears. The amount of dust, in turn, relates to how much gas is being produced, because the gas carries the dust particles off the nucleus. So bright comets are usually active comets, producing substantial amounts of gas. Dim comets are usually less active, producing less gas and dust. But 3I/ATLAS presented a puzzle. When astronomers measured its brightness, they found it was quite luminous for an object of its size at its distance from the Sun. Based on its brightness, they could estimate how much dust was in the coma. But when they measured the gas production using spectroscopy, looking at the characteristic emission lines of molecules like cyanide and hydroxyl radicals that indicate water sublimation, the numbers didn't match. The comet appeared to be producing less gas than expected for its brightness. Significantly less. The ratio of dust to gas was unusually high, perhaps 10 times higher than typical comets. It was as if 3I/ATLAS was somehow releasing a lot of dust without the corresponding amount of gas that should be carrying that dust away from the nucleus. Now, comets do vary in their dust-to-gas ratios. This isn't entirely unprecedented. Some comets are naturally more dusty than others, depending on their formation history and composition. But the ratio observed in 3I/ATLAS was at the extreme end of what had been seen before, high enough to prompt questions about whether it was really just a natural variation or whether something else was going on. One possibility was that the measurements were wrong. Measuring gas production from a faint distant comet is technically challenging. The spectroscopic signals are weak, and you have to carefully account for the comet's distance, the observing conditions and various instrumental effects. Perhaps the gas production was being underestimated, and the comet was actually more normal than it appeared. But multiple independent teams made similar measurements using different telescopes and techniques, and they all found the same thing: an unusually high dust-to-gas ratio. The consistency across different observations made it less likely that this was simply an error or artifact of the measurements. Another possibility was that 3I/ATLAS was depleted in volatile ices compared to typical comets. If its nucleus was predominantly made of less volatile materials, substances that required more heating to sublimate, it might produce less gas for a given amount of solar radiation. But this raised its own questions. Why would an interstellar comet be so depleted? Comets from our own Oort cloud, which spend most of their time at similarly cold distances from the Sun, aren't unusually depleted. What would make an interstellar comet different? Some researchers proposed that 3I/ATLAS might have passed close to another star before entering our solar system, receiving enough heating to drive off its most volatile ices. This was plausible. If the comet had spent the last million years travelling through interstellar space after being ejected from a solar system where it had already made close passes to that system's star, it might have been partially processed, already having lost some of its most easily sublimated materials. But there was another possibility that some scientists began to consider, one that was more speculative but worth examining. What if the brightness wasn't entirely from reflected sunlight off natural dust? What if something about the object's surface or structure was contributing to its appearance in ways that didn't fit the standard comet model? This wasn't to suggest anything particularly exotic, just that perhaps the assumptions about what creates a comet's brightness needed revision. Maybe the dust particles had unusual properties, unusual sizes or compositions that made them reflect light more efficiently than typical comet dust. Maybe the nucleus itself had exposed ice that contributed to the brightness without producing much detectable gas yet. Or maybe, a few researchers quietly wondered, the object wasn't entirely natural. Not in the sense of being an alien spacecraft, which seemed vanishingly unlikely, but perhaps something artificial from another civilization, though still basically inert, travelling through space for who knows how long. A probe, a piece of debris, something manufactured that happened to outgas slightly as it warmed, creating a comet-like appearance but with unusual properties because it wasn't actually made of ice and rock. This last possibility wasn't taken seriously by most astronomers. The evidence was far from sufficient to justify such an extraordinary conclusion, but it was mentioned quietly in a few scientific papers and conference presentations, because one of the things that makes science work is the willingness to consider even unlikely possibilities when the data doesn't quite fit expectations. As long as you don't claim certainty without evidence, asking questions is valuable, and scientists were certainly asking questions about 3I/ATLAS. To understand why 3I/ATLAS generated so much interest, it's helpful to compare it with Oumuamua, that first confirmed interstellar visitor that had captivated astronomers and the public alike 2 years earlier. The two objects were remarkably different, and yet both had characteristics that defied easy explanation. Oumuamua was discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Its name comes from Hawaiian and means roughly scout or messenger from the distant past. Unlike 3I/ATLAS, Oumuamua showed no signs of outgassing, no coma, no tail, no spectroscopic evidence of sublimating ice. It looked like an asteroid, not a comet, a bare rock tumbling through space. But Oumuamua was peculiar in several ways. First, its light curve, the pattern of brightness changes as it rotated, suggested an extremely elongated shape, something like a cigar or possibly a disc, with an aspect ratio of perhaps 10:1. No object in our solar system has such an extreme shape. Most asteroids are relatively round or irregular but not dramatically elongated. Second, as Oumuamua left the inner solar system, careful tracking revealed that it was accelerating slightly, moving a bit faster than it should have if only the sun's gravity was affecting it. This non-gravitational acceleration was tiny but clearly present in the data. For a comet, such acceleration would be normal, explained by outgassing. But Oumuamua showed no signs of outgassing, so what was pushing it? Various explanations were proposed. Perhaps Oumuamua was outgassing, but in a way that didn't produce a visible coma, maybe releasing pure hydrogen that wouldn't show up in normal observations. Perhaps it was being pushed by sunlight reflecting off its surface. Though calculations suggested its reflectivity would need to be extremely high for this to work. Perhaps some other natural process was at play that we simply hadn't encountered before. But in late 2018, a respected Harvard astronomer named Abraham Loeb published a paper with a colleague suggesting that Oumuamua might be artificial. Specifically, they proposed it could be a light sail, a large thin sheet designed to be pushed by sunlight, the kind of propulsion system that humans have discussed building for interstellar travel. The paper was careful not to claim this was definitely the case, but it argued that the possibility should be considered and that Oumuamua's properties were at least consistent with such an explanation. The paper generated enormous controversy. Many astronomers criticised it as premature and sensational, arguing that exotic explanations should only be considered after all natural explanations have been exhausted, and that there were still natural phenomena that could potentially explain Oumuamua's behaviour. Others defended the right to explore all possibilities, even unlikely ones, as long as you're clear about the level of speculation involved. The debate about Oumuamua was still ongoing when 3I/ATLAS appeared, and now there was a second interstellar object with unusual properties, different unusual properties to be sure, where Oumuamua was inactive and oddly shaped. 3I/ATLAS was active and appeared more conventionally comet-like, but the unusually high dust-to-gas ratio added to a growing sense that interstellar objects might not behave exactly like the asteroids and comets native to our solar system. This shouldn't be entirely surprising. Objects from other star systems formed in different environments, around stars with different compositions, in protoplanetary disks with different temperatures and densities. There's no reason to expect perfect uniformity across all solar systems. Just as exoplanets have surprised us with their diversity, including types of planets that don't exist in our solar system at all, interstellar objects might show us varieties of asteroids and comets we haven't encountered among our local population. But the question remained, were the unusual properties of Oumuamua and 3I/ATLAS just natural variations? Examples of the diversity we should expect? Or was something else going on? Were we perhaps seeing the debris from technological civilizations scattered across the galaxy over millions of years? Not active spacecraft, but derelict probes, dead satellites, fragments of megastructures, the kind of things that an advanced civilization might create and that might eventually escape into interstellar space. The honest answer is that we don't know. 2 objects isn't a large enough sample size to draw firm conclusions about interstellar populations. We need more data. We need to detect dozens or hundreds of interstellar visitors and study their properties in detail. Then we'll be able to say whether Oumuamua and 3I/ATLAS were strange outliers or representative of what exists between the stars. As we continue deeper into this journey, let's explore what else scientists learned about 3I/ATLAS, what they found when they looked at its composition, its structure, its trajectory, and the subtle ways it behaved as it swept through our solar system. Each observation added another piece to a puzzle that remains incompletely solved. One of the most powerful tools astronomers have for understanding distant objects is spectroscopy, the technique of splitting light into its component wavelengths and analysing the patterns that appear. Every element and molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint that can be read across vast distances. When light from 3I/ATLAS was passed through spectrographs on Earth-based telescopes, those fingerprints began revealing the comet's composition. The first spectroscopic observations came in late August 2019, about 2 weeks after the initial discovery. Multiple observatories pointed their instruments at the comet, which was still quite faint but brightening as it approached the sun. The spectra showed emission lines characteristic of typical comets: cyanide, carbon monoxide, hydroxyl radicals produced from the breakdown of water molecules, and other familiar signatures. Cyanide in particular is often used as a tracer for comet activity because its emission line is relatively strong and easy to detect. Despite its deadly reputation on Earth, cyanide is common in comets, locked into organic molecules that formed in the cold outer regions of protoplanetary disks. When these molecules are released by sublimating ice and broken apart by solar ultraviolet light, they produce that characteristic emission that astronomers can measure. The presence of these familiar molecules suggested that 3I/ATLAS was indeed a comet in the traditional sense, composed of ice and organic material similar to comets from our own Oort cloud. Its formation environment, whatever star system it came from, apparently produced similar chemistry to our own solar nebula. This made sense given that the basic ingredients, hydrogen, carbon, oxygen, nitrogen, are common throughout the galaxy, and the physics of how protoplanetary disks cool and condense should be similar everywhere. But when researchers calculated the production rates of these molecules based on the strength of the spectroscopic lines, they again encountered that puzzling ratio. The amount of cyanide and other gas phase molecules seemed lower than expected given the comet's brightness and estimated dust production. It was that same discrepancy noticed before, now confirmed with detailed chemical measurements. Some teams also looked for less common molecules that might provide clues to the comet's origin. They searched for emission lines from various carbon chains and other organic species. They looked for isotopic ratios, comparing the amounts of different isotopes of carbon, nitrogen and other elements, which can reveal information about the temperature and conditions during formation. The hope was that 3I/ATLAS might show isotopic ratios different from solar system comets, offering a clear chemical signature of its extrasolar origin. But the results were inconclusive. The comet was faint enough that detecting subtle differences in isotopic ratios was at the limit of what current telescopes could do. Some papers reported tentative detections of unusual ratios, but others found values consistent with solar system comets within the measurement uncertainties. More sensitive observations would have been needed to say definitively whether 3I/ATLAS's chemistry was truly alien. Another interesting aspect of the spectroscopic observations was the temporal variation. Comets don't outgaze uniformly. As the nucleus rotates, different regions face the sun, and if the surface has patches of different composition or different amounts of exposed ice, the outgassing rate can change over time. For 3I/ATLAS, some observations suggested variations in the emission line strengths over periods of hours to days. This variability is normal for comets. But for 3I/ATLAS, combined with the unusual dust-to-gas ratio, it raised questions about the nucleus's structure. Was the surface particularly heterogeneous, with icy patches surrounded by dusty regions? Was the nucleus perhaps fragmenting, breaking apart as it warmed, which would expose fresh surfaces and change the outgassing pattern? Or was something else creating the variations? Fragmentation is worth considering because comets do sometimes break apart, particularly when they're making their first close pass to the sun, or when they've been weakened by previous approaches. The thermal stress of rapid heating combined with the internal pressure from gas trying to escape can crack the nucleus. Sometimes comets split into multiple pieces, each continuing along similar trajectories but gradually drifting apart. Other times they disintegrate more completely, spreading into a cloud of debris. Astronomers watched 3I/ATLAS carefully for signs of fragmentation, but saw nothing definitive during its passage. The comet remained intact as a single object, though whether small pieces might have broken off undetected is difficult to say. Small fragments wouldn't necessarily be visible unless they were large enough to develop their own comas, and the resolution of telescopes observing something so distant makes it hard to see fine details. The spectroscopic data, taken together, painted a picture of a comet that was mostly normal, but with subtle peculiarities. It had the chemical composition expected of a comet. It was outgassing and producing familiar molecules. but the amounts of those molecules relative to the dust production suggested something slightly different from the typical solar system comet. Whether this difference was significant enough to indicate anything truly unusual, or just natural variation, remained an open question as observations continued through the fall of 2019. Determining the actual size and shape of 3I/ATLAS's nucleus presented significant challenges. The comet was surrounded by its Coma, that bright cloud of gas and dust that extended far beyond the nucleus itself. Seeing through the Coma to resolve the solid nucleus requires either getting very close, which wasn't possible for this rapidly moving interstellar visitor, or using techniques that can distinguish the nucleus's contribution to the overall brightness from the contribution of the surrounding Coma. The most direct way to measure a comet's nucleus is through imaging at very high resolution. When spacecraft visit comets up close, as missions have done for several solar system comets, they can photograph the nucleus in stunning detail, revealing its shape, size, surface features, and active regions. But no spacecraft reached 3I/ATLAS. It was discovered too late for any existing mission to intercept it, and by the time space agencies could have launched something, the comet would be long gone. From Earth, even with the largest telescopes, 3I/ATLAS appeared as a fuzzy blob, its nucleus unresolved within the brightness of the Coma. Astronomers therefore had to use indirect methods to estimate the nucleus's size. They could model how much sunlight the Coma should be reflecting based on assumptions about the dust particles' properties, and use that to subtract the Coma's contribution from the total brightness, leaving an estimate of the nucleus's brightness. From the nucleus's brightness and assumptions about how reflective its surface might be, they could then estimate its size. These calculations suggested that 3I/ATLAS had a nucleus roughly 1/2 kilometre to perhaps 2 kilometres in diameter. The uncertainty range is large because it depends on the assumed reflectivity, or albedo, of the surface. Comet nuclei tend to be quite dark, with albedos of just a few percent, darker than charcoal. Because the organic material that covers their surfaces absorbs most light. But the exact value can vary, and without direct measurements you're making an educated guess. A nucleus in the 1/2 kilometre to 2 kilometre range would make 3I/ATLAS a small to medium-sized comet, comparable to many comets from our own solar system. Not a giant like Hale-Bopp, which had a nucleus estimated at 60 kilometres across, but not a tiny fragment either. A respectable size for something that had travelled light years through interstellar space. But there was an interesting detail that some researchers noted. If you assumed 3I/ATLAS had a more reflective surface than typical comets, say an albedo of 10 or 15% instead of 3 to 5%, the estimated size would be smaller. With a higher albedo, you wouldn't need as much surface area to produce the observed brightness. The nucleus could be just a few hundred metres across, still large but at the small end of what you'd expect for such an active comet. Why might 3I/ATLAS have a more reflective surface? Most comets darken over time as they make repeated passes near the Sun. The solar radiation and heat break down the organic compounds on the surface, leaving behind a dark, carbon-rich crust. But 3I/ATLAS was likely making its first pass into the inner regions of any solar system in millions or billions of years. Its surface might be relatively fresh, covered with frost or less processed organic material that reflects more light. Alternatively, if the nucleus was fragmenting or had recently shed an outer layer, fresh ice could be exposed, which would be quite bright compared to the typical dark comet surface. Ice can have an albedo of 50% or more, though it would quickly darken as the solar wind and radiation processed it, and as dust settled on it from the outgassing. Determining the shape of the nucleus was even more difficult. For objects in our solar system, astronomers can track brightness variations over time as the object rotates, and the pattern of these variations reveals information about the shape. An elongated object, for instance, will appear brighter when its long axis is pointing toward us, and dimmer when we see it end on, creating a periodic variation in brightness with each rotation. For 3I/ATLAS, some observations suggested brightness variations over a period of several hours which could indicate rotation. But the variations were small and partly contaminated by real changes in the outgassing rate, making it hard to separate the rotation signal from actual physical changes in how active the comet was. The rotation period, if the variations were indeed from rotation, seemed to be somewhere between 6 and 12 hours, which would be typical for a comet of this size. As for the actual shape, there simply wasn't enough data to say. The nucleus could be roughly spherical, or it could be elongated, or it could be irregular like most small solar system bodies, which tend to look more like potatoes than spheres because their gravity is too weak to pull them into round shapes. Without higher resolution imaging or more detailed photometry, the shape remained unknown. The uncertainty about the nucleus's size and shape contributed to the uncertainty about what 3I/ATLAS really was. A small, bright nucleus might behave differently than a large, dark one. It might fragment more easily, or outgas more efficiently, or have different thermal properties. Every assumption built on every other assumption, creating a chain where errors could compound. Astronomers working on 3I/ATLAS were acutely aware of these limitations and tried to be careful about not over-interpreting their data. Still, they could at least say that 3I/ATLAS had a solid nucleus of some kind, a few hundred meters to a couple of kilometers across, rotating over a period of hours and surrounded by an active coma. That much was clear from the observations, even if the precise details remained frustratingly uncertain. Understanding exactly where 3I/ATLAS came from and where it was going required meticulous tracking of its position over many weeks. Every observation added to the dataset, allowing astronomers to refine the orbital parameters and trace the object's path backward and forward through time. This trajectory analysis revealed some fascinating details about the comet's journey through the galaxy. When you calculate an orbit using observations from only a few nights, the uncertainty is large. The object might be on one of many possible paths that all fit the limited data roughly equally well. But as more observations accumulate from different positions in Earth's orbit, the uncertainty shrinks. The true orbit becomes clearer, and you can project it with increasing confidence into the past and future. For 3I/ATLAS, the tracking data showed it was approaching the Sun from the direction of the constellation Cassiopeia. Its velocity relative to the Sun's rest frame, the so-called barycentric velocity, was about 31 kilometers per second. This is the speed it had before the Sun's gravity started accelerating it inward. That's quite fast by everyday standards, but actually fairly typical for interstellar objects, which move at speeds comparable to the Sun's own motion through the galaxy. Tracing the trajectory backward, researchers could estimate where the comet had been in the relatively recent past. 1 million years ago, it would have been several light-years from our solar system. Travelling through the cold interstellar medium between stars. 10 million years ago, it would have been tens of light-years away, passing through a completely different region of the galactic neighbourhood. And beyond that, the uncertainties grow large, making it impossible to say with confidence which stellar system might have been its birthplace. One interesting question was whether 3I/ATLAS had passed particularly close to any nearby stars in the recent past. If it had, that encounter might have altered its trajectory, changing its speed or direction. A close stellar passage could also have heated the comet, driving off volatile ices and potentially explaining its unusual composition. Several research groups ran the trajectory backward through databases of stellar positions and motions. Looking for close encounters, they found a few possibilities. There were a handful of stars that 3I/ATLAS might have passed within a light-year or so of in the past few million years, though the uncertainties in both the comet's trajectory and the star's motions made it hard to be certain. None of these potential encounters were close enough to have dramatically heated the comet. The comet would have had to pass within a small fraction of a light year for that. But they might have slightly perturbed its path. Looking forward, the calculation showed that 3I/ATLAS would leave our solar system on a trajectory that would take it out toward the constellation of Telescopium. It would pass back through the plane of the Milky Way in a few tens of thousands of years and continue wandering through the galaxy indefinitely, unless it happened to encounter another star system. Given the vast spaces between stars, the odds of any particular star encounter are small. More likely, 3I/ATLAS will travel for millions or billions more years through the interstellar void before chance brings it near another planetary system. But there was a subtlety in these trajectory calculations that some researchers found intriguing. The calculated orbit depended on accounting correctly for all forces acting on the comet. Gravity from the Sun was the dominant force. But there were also smaller perturbations from the planets, particularly Jupiter, whose gravitational influence extends quite far. And for a comet, there was the non-gravitational acceleration from outgassing. To get the trajectory right, you need to model the outgassing force. You estimate how much gas is being produced based on the comet's brightness and activity level, and you calculate how that gas production creates thrust as the gas jets away from the nucleus. For solar system comets, this process is well understood, and the non-gravitational effects can be predicted reasonably well. But for 3I/ATLAS, with its unusual dust-to-gas ratio, the modelling was less certain. If the comet was producing less gas than a typical comet of its brightness, the non-gravitational force might be smaller than initially assumed. This would affect the calculated orbit, shifting the estimated path slightly. Not dramatically, the effect is small, but enough that researchers had to include estimates of the uncertainty in their trajectory calculations. Some papers noted that the non-gravitational acceleration seemed smaller than expected for a comet of 3/ATLAS's apparent activity level. This was consistent with the reduced gas production suggested by the spectroscopy, but it added another piece to the puzzle. Why would a comet show signs of activity, a bright coma and dust production, but experience less outgassing-induced acceleration? One explanation again was that the nucleus was fragmenting. If pieces were breaking off, they might contribute to the coma's brightness but wouldn't create directional thrust the way a jet of gas from the nucleus would. The fragments would carry dust and perhaps some ice, adding to the overall cloud of material surrounding the comet, but the gas released from the fragments would be distributed more symmetrically and wouldn't accelerate the main nucleus in any particular direction. Another possibility was that the outgassing was not concentrated in jets, but was instead quite uniform across the nucleus's surface. Jets create stronger non-gravitational forces because they're directional. Uniform outgassing, by contrast, produces forces that partly cancel out, reducing the net acceleration. If 3I/ATLAS had a relatively smooth outgassing pattern, that might explain the weaker-than-expected non-gravitational acceleration. Or perhaps that same small group of researchers wondered the object wasn't outgassing as actively as it appeared, and the coma was being created by some other process. What that other process might be was unclear, but in science, when your observations don't quite match your models, you're supposed to question both the observations and the models. The trajectory data, combined with the spectroscopy and photometry, created a complex picture. 3I/ATLAS was clearly a real object from interstellar space, that much was beyond doubt. But the details of its behaviour kept presenting small discrepancies that didn't quite fit the simple story of a normal interstellar comet passing through the inner solar system. Another line of investigation involved analysing the colour of 3I/ATLAS's coma, meaning the way its brightness varied across different wavelengths of light. This colour information can reveal the properties of the dust particles in the coma, their sizes, shapes and compositions, which in turn tell you something about the comet's nucleus and formation history. When sunlight reflects off dust particles, the efficiency of that reflection depends on the particle's size relative to the wavelength of light. Very small particles, smaller than the wavelength of visible light, scatter blue light more efficiently than red light, which is why Earth's sky is blue. Larger particles scatter all wavelengths more equally, appearing whiter or redder depending on their material properties. By measuring how much light the coma reflects at different wavelengths, you can estimate the typical dust particle size. For 3I/ATLAS, observations in different colour filters showed that the coma was relatively neutral in colour, meaning it reflected different wavelengths fairly equally. This suggested that the dust particles were relatively large, perhaps micrometers to tens of micrometers in diameter, comparable to the wavelength of visible light or larger. This is typical for comets. The dust lifted off comet nuclei tends to be in this size range, because smaller particles are more easily swept away by the solar wind and radiation pressure, while larger particles fall back to the nucleus. But there were subtle colour variations in different parts of the coma and at different times. Some observations showed the coma appearing slightly redder at certain wavelengths, suggesting a particular composition of the dust grains. Comets can have dust grains made of silicates, similar to sand or organic compounds or mixtures of the two. The exact composition affects the colour, with organic-rich dust tending to be darker and redder. Comparing 3I/ATLAS's colour to solar system comets, researchers found it was broadly similar but perhaps slightly redder on average. This could indicate a higher fraction of organic material in the dust, or it could be a natural variation that falls within the range seen in our own cometary population. Without more detailed spectroscopic analysis of the dust itself, which is challenging to do from Earth, it was hard to say for certain. One aspect that particularly interested some researchers was the colour of the nucleus itself, or rather, the attempt to measure it. If you could separate the nucleus's contribution from the coma's contribution to the overall light, you could determine the nucleus's colour independently. For 3I/ATLAS, this was difficult given the brightness of the surrounding coma, but some teams attempted it by modelling the coma and subtracting it from the observations. The results suggested that the nucleus might be redder than typical comet nuclei from our solar system. Comet nuclei are generally very red, as red or redder than many asteroids, due to the organic compounds on their surfaces. But 3I/ATLAS seemed to be at the extreme red end of the distribution. This could mean its surface was particularly rich in complex organic molecules, or that it had been exposed to different radiation environments during its long journey through space. Cosmic rays and ultraviolet light from the interstellar radiation field can gradually alter the chemistry of organic materials on an object's surface over millions of years. This process, called space weathering, tends to darken and redden surfaces. For an object that had been travelling through interstellar space for potentially billions of years since being ejected from its home system, space weathering could have significantly modified the surface layer. But there's a complication with this interpretation. Once the comet started actively outgassing and shedding its surface layer, fresh material from beneath would be exposed. This fresh material might not have the same weathered appearance. The fact that 3I/ATLAS appeared active meant its surface was changing, potentially exposing less weathered material that should be less red. Yet the observation suggested a red colour. One way to reconcile this was if the nucleus was fragmenting. Fragments broken off recently from the interior would expose fresh surfaces, but if the whole nucleus had a relatively uniform composition rich in organic material, the fragments would still appear red even without space weathering. Alternatively, maybe the outgassing was gentle enough that it wasn't completely stripping the surface, leaving some of the weathered material intact even as the comet became active. The colour analysis also extended to looking for any unusual spectral features, specific wavelengths where the coma or nucleus absorbed or reflected light differently than expected. These features could indicate unusual minerals or chemical compounds. Researchers searched for them carefully, hoping to find a definitive sign of an exotic composition that would clearly mark 3I/ATLAS as different from solar system objects. They didn't find anything dramatic. The spectral features were broadly consistent with typical comets and asteroids. But subtle differences were present, enough to keep the question open. Without a spacecraft visit or much more detailed observations than were possible with Earth-based telescopes observing such a faint, distant object, definitively characterizing 3I/ATLAS's composition remained just out of reach. As fall turned to winter in 2019, 3I/ATLAS continued its journey toward the Sun, brightening gradually but never becoming spectacular. Ground-based telescopes and some space-based observatories tracked it as best they could, gathering data that would be analysed and reanalysed in papers published over the following years. And as we'll see, some of those analyses would propose ideas that went beyond conventional cometary science. The discovery of 3I/ATLAS came just 2 years after Oumuamua, suggesting that interstellar objects might pass through the inner solar system more frequently than astronomers had previously thought. This realization sparked an intensification of survey efforts and discussions about how to better detect these fleeting visitors. If we could find more interstellar objects and study them in detail, we could start to understand the population, distinguishing what's typical from what's unusual. Several major survey projects were already underway or in planning stages. The Large Synoptic Survey Telescope, later renamed the Vera-C. Rubin Observatory was under construction in Chile and promised to revolutionize the detection of transient and moving objects when it came online. With its enormous camera and wide field of view, it would image the entire visible sky every few nights, creating a continuously updated map that would reveal anything that moved or changed. Simulations suggested that once the Rubin Observatory became operational, it should detect 1 to 2 interstellar objects per year passing within the orbit of Jupiter. Some years might yield more, some fewer, but over a decade of operation, we could build up a substantial catalogue. Each detection would be an opportunity to gather data on composition, shape, trajectory, and behaviour, building a statistical picture of what exists in the interstellar medium. Other facilities were also contributing. The Atlas survey that discovered 3I/ATLAS operates multiple telescopes that scan the sky nightly for near-Earth asteroids. While its primary mission is planetary defense, identifying potential impactors, it naturally also detects other interesting objects. Pan-STARRS, which found Oumuamua, continued its survey work, and space-based telescopes, though not designed specifically for finding such objects, occasionally captured data useful for characterizing them. But there was a timing challenge. Interstellar objects move quickly through the solar system. By the time you detect one, confirm its interstellar nature, and organize follow-up observations, it may be already departing. Oumuamua had been discovered as it was leaving, giving astronomers only a few weeks to study it before it became too faint. 3I/ATLAS was discovered earlier in its approach, providing more time, but even so there were limits to what could be learned with current technology. This realization led to discussions about dedicated missions to intercept interstellar objects. If you knew an object was coming and had enough warning, you could launch a spacecraft to rendezvous with it, study it up close, and perhaps even land on it or collect samples. The European Space Agency investigated the concept, examining what kind of propulsion system would be needed to catch up to an object moving at tens of kilometers per second relative to the Sun. The conclusion was that with current propulsion technology, you'd need years of advance warning to successfully intercept an interstellar object, detect it when it's still several astronomical units away, while there's still time to launch and accelerate a spacecraft to match its trajectory. This would require sensitive surveys capable of detecting very faint objects far from the Sun, much fainter than current surveys can routinely spot. Future technology might help. If we develop more powerful propulsion systems, perhaps using nuclear rockets or advanced ion drives, the required warning time could decrease. Or if we maintain a spacecraft in a prepared state, ready to launch quickly, we could respond faster to a newly detected object. But these approaches require significant investment and planning. In the meantime, astronomers make do with remote observations, squeezing as much information as possible out of the photons that reach our telescopes, and they remain alert for the next visitor, knowing that each one is a precious opportunity to glimpse what exists beyond our solar neighbourhood. Some researchers also wondered whether objects like Oumuamua and 3I/ATLAS might have smaller companions. If a comet from another star system broke apart during its ejection process or along its journey, the fragments would follow similar trajectories, perhaps passing through our solar system in a loose cluster. Detecting such companions would be valuable, offering multiple samples from the same parent body, or at least from the same stellar system. Searches for companions near Oumuamua and 3I/ATLAS turned up nothing. As far as could be determined, each object travelled alone, but the sensitivity of the searches was limited. Smaller fragments, or pieces that had separated years earlier and drifted slightly apart, might have been present but undetectable. It's something to keep in mind for future observations, to look not just for a single interstellar object but for possible groups. The broader context is that our solar system is constantly being visited by interstellar material, though most of it is too small to detect. Interstellar dust grains, particles just micrometers across, constantly drift through the solar system, detectable only with specialized instruments on spacecraft. The Ulysses spacecraft, which orbited the Sun out of the plane of the planets, detected streams of interstellar dust in the 1990s. More recently, the Parker Solar Probe, diving close to the Sun, has detected similar particles. These dust grains are fragments of larger objects, debris from collisions in other star systems or material shed by comets. They fill the interstellar medium with a tenuous haze that larger objects like Oumuamua and 3I/ATLAS occasionally emerge from. By studying both the grains and the larger objects, we're beginning to understand what the space between stars contains, the census of debris left over from billions of years of planetary system evolution throughout the galaxy. The question of whether 3I/ATLAS could be anything other than a natural comet was not one most scientists spent significant time on. The overwhelming majority of astronomers studying the object assumed it was natural, a chunk of ice and rock from another solar system, behaving in ways that might be unusual but were still within the realm of natural cometary processes. But a small minority raised the possibility that it, like Oumuamua before it, might warrant consideration of alternative explanations. The case for considering artificial origins didn't rest on any single dramatic observation. There was no clear evidence of signals being transmitted, no obviously manufactured structures visible, no behaviour that screamed spacecraft. Instead, it was the accumulation of small anomalies, the unusual dust-to-gas ratio, the brightness inconsistent with measured gas production, the weak non-gravitational acceleration, the potentially unusual surface properties. Each anomaly could be explained naturally, but together they painted a picture that was at least slightly incongruous. One researcher, building on the earlier work on Oumuamua, published a paper examining whether 3I/ATLAS's properties could be consistent with a thin artificial structure, perhaps a derelict light sail or the remains of some other interstellar probe. The paper didn't claim this was definitely the case, but argued that the possibility shouldn't be dismissed without careful analysis. After all, if technological civilizations exist elsewhere in the galaxy and have been present for millions or billions of years, their artifacts could be scattered through space, and we should at least consider what signatures such artifacts might produce. A light sail is a large, thin sheet designed to be pushed by radiation pressure from starlight. Humans have experimented with small versions and have proposed building larger ones for interstellar travel. Such a device would need to be extremely thin and light to achieve high accelerations from sunlight pressure. If a light sail from another civilization were tumbling through space, perhaps damaged or derelict, it might outgaze slightly as it warmed. particularly if it had accumulated a coating of interstellar ice or organic material during its journey. This outgassing could create a comet-like appearance without the object being a natural comet. The dust-to-gas ratio anomaly could potentially be explained by this scenario. If most of the brightness came from the reflective sail material rather than from dust particles, while only a small amount of actual outgassing occurred from surface contamination, the ratio would appear skewed. Similarly, the non-gravitational acceleration might be different because the dominant force would be radiation pressure on the sail rather than outgassing thrust. Critics of this idea pointed out several problems. First, there was no direct evidence of any artificial structure. The observation showed what looked like a comet, with spectroscopic signatures of typical cometary molecules. If there was a light sail, where was the ice that was outgassing attached? You'd need a substantial amount of ice to produce the observed coma, and that ice would presumably be sitting on the sail, but then you'd essentially have a natural comet-like object that happened to have a thin sheet underneath it, which seems unnecessarily complicated. Second, the sail hypothesis didn't really explain the observations better than natural processes. Yes, natural processes left some questions, but invoking an artificial object introduced many more questions. How did interstellar ice accumulate on a manufactured surface? Why would a damaged sail still be intact enough to hold ice? Where did this thing come from, and how long had it been travelling? The natural explanation, while imperfect, was at least simpler and required fewer assumptions. Third, there was the issue of probability. Technological civilizations capable of building interstellar craft are presumably rare. Even if they exist, the number of derelict probes they've launched into the galaxy is hard to estimate, but likely small compared to the number of natural objects ejected from planetary systems. Every star system ejects material during planet formation, producing countless asteroids and comets wandering the galaxy. Only a tiny fraction of star systems, if any, produce technological civilizations that build space probes. So natural objects should vastly outnumber artificial ones, making it far more likely that any given interstellar visitor is natural. However, proponents argued that we can't make firm statements about probabilities when we don't know how common technological civilizations are or how prolifically they build probes. If civilizations are common and long-lived, and if they've been sending probes into space for millions of years, the galaxy could have accumulated substantial numbers of such objects. Not enough to make every interstellar visitor artificial, but perhaps enough that out of dozens or hundreds of detected interstellar objects, one or two might be. The scientific method is supposed to be open to all possibilities, testing them against observations without prejudice. But it also incorporates the principle that extraordinary claims require extraordinary evidence. Claiming that an object is artificial is an extraordinary claim because it implies the existence of another technological civilization, which would be one of the most significant discoveries in human history. Therefore, the evidence needs to be compelling enough to rule out all plausible natural explanations. For 3I/ATLAS, the evidence wasn't that compelling. The anomalies were real, but not dramatic. Natural explanations, while requiring some special pleading or invoking processes we don't fully understand, were still viable. Most scientists concluded that 3I/ATLAS was almost certainly a natural comet, perhaps one with unusual properties due to its interstellar origin and formation in a different stellar environment, but natural nonetheless. Still, the discussion was valuable because it pushed researchers to carefully examine their assumptions. What should a comet from another star system look like? How different could it be from solar system comets, while still being explicable by natural processes? At what point would evidence genuinely favour an artificial explanation? These are questions worth thinking about, even if the answers for 3I/ATLAS firmly point toward nature. Among the natural explanations for 3I/ATLAS's unusual properties, the idea that the nucleus was fragmenting gained considerable attention. Comets do break apart, sometimes spectacularly, and fragmentation could potentially explain several of the observed anomalies. Let's explore what fragmentation entails and whether it fits the evidence. Comet nuclei are not solid blocks of ice. They're more like loosely consolidated rubble piles, collections of ice chunks, dust and rock held together by a combination of their own weak gravity and the tensile strength of the ice. As a comet approaches the sun and warms, the ice sublimates, creating internal pressure as gas tries to escape. If the nucleus has cracks or weak points, this pressure can force the pieces apart. Thermal stress also plays a role. The side of the nucleus facing the sun heats up, while the opposite side remains cold. This differential heating creates stresses that can crack the ice. Combine that with the spin of the nucleus and the centrifugal forces trying to fling material outward, and you have multiple mechanisms that can lead to fragmentation. When a comet fragments, several things happen. First, the fragments separate, each now an independent object but initially following very similar orbits. Over time, as they experience slightly different forces from outgassing and radiation pressure, the fragments drift apart. Observers might see multiple distinct nuclei, or, if the fragments are small or still close together, a single elongated or irregular coma. Second, fragmentation exposes fresh ice that was previously interior to the nucleus. This fresh ice sublimates vigorously, often causing a dramatic increase in brightness. Many comets that have been observed to fragment showed sudden brightening episodes coinciding with the breakup. The newly exposed surface area releases gas rapidly, creating a larger coma and potentially a more prominent tail. Third, the dust-to-gas ratio can change. The fragments, being smaller, have higher surface area to volume ratios, meaning they can heat up more quickly and release gas more efficiently than a single large nucleus. However, if the fragments also include rocky or dusty material, they might shed dust without producing proportionally more gas, potentially altering the dust-to-gas ratio in complicated ways, depending on the composition of the material being exposed. For 3I/ATLAS, several observations were consistent with fragmentation. The unusual brightness relative to gas production could be explained if fresh ice was exposed, but the gas hadn't fully escaped yet, temporarily making the comet brighter than its gas production would suggest. The weak non-gravitational acceleration could result from the forces being distributed among multiple fragments, rather than acting on a single nucleus, diluting the net effect. Some photometric observations suggested possible irregularities in the coma's brightness distribution, hints that there might be multiple sources of material rather than a single point. But the resolution wasn't good enough to confirm this definitively. If the fragments were still close together, separated by only a few kilometers or less, Earth-based telescopes couldn't resolve them individually. Researchers also looked at the timeline of observations, searching for sudden changes that might indicate a fragmentation event. They found some evidence of variability, periods where the brightness increased more quickly than expected, or where the coma's appearance changed. These could be interpreted as fragmentation episodes, though they could also be natural variations in outgassing from a single intact nucleus with an uneven surface. One challenge with the fragmentation hypothesis is that it's somewhat unfalsifiable. If you observe anything unusual, you can invoke fragmentation to explain it. The nucleus broke apart, and that's why things look odd. Without direct imaging showing multiple distinct nuclei, it's hard to prove or disprove fragmentation conclusively. You're left with circumstantial evidence and arguments about what's more plausible. But fragmentation is a known phenomenon. Comets do break apart. Some famous examples include Comet Shoemaker-Levy 9, which fragmented into multiple pieces that then crashed into Jupiter in 1994, and Comet Schwarzmann-Wachmann 3, which split into dozens of fragments during a close solar approach. So invoking fragmentation for 3I/ATLAS isn't reaching for an exotic explanation. It's suggesting something that happens regularly, at least to solar system comets. However, there's a question of timing. Why would 3I/ATLAS fragment during this particular passage if it had presumably survived intact for millions or billions of years of travel through interstellar space? One answer is that the stresses of approaching a star and heating up for the first time in eons were more than the loosely held together nucleus could withstand. The comet might have been stable in the cold of interstellar space, but vulnerable once subjected to solar heating. Another possibility is that 3I/ATLAS had made previous close stellar passages in the past, perhaps passing near the star it was ejected from or near other stars along its journey, and those passages had weakened it. Cracks formed during earlier heating cycles could have propagated over time, leaving the nucleus in a fragile state that finally gave way during its passage through our solar system. If the fragmentation hypothesis is correct, it suggests that interstellar comets might be more fragile than their solar system counterparts, perhaps because they lack the repeated heating and cooling cycles that could sinter the ice and strengthen the structure. Or perhaps they're simply old, weakened by eons of cosmic ray bombardment and micrometeorite impacts during their long journey through space. These are testable ideas once we have more interstellar objects to study and can look for patterns in how they behave as they warm. For now, fragmentation remains one of several plausible explanations for 3I/ATLAS's properties, neither proven nor ruled out, a reminder of how difficult it is to draw definitive conclusions from limited data on a distant, transient object. Beyond the questions of activity and behaviour, scientists were deeply interested in what 3I/ATLAS was actually made of. Its composition could provide direct evidence of its origin, revealing whether the conditions in its formation environment were similar to or different from our own solar system. Let's examine what the observations told us about the materials making up this interstellar visitor. The spectroscopy, as mentioned, showed familiar molecules: cyanide, carbon monoxide, hydroxyl radicals, and traces of various carbon-bearing species. These are all common in solar system comets. The presence of water, inferred from the hydroxyl emissions, suggested that water ice was a major component, just as it is in comets from the Kuiper belt and Oort cloud. Carbon monoxide, another common cometary ice, appeared in the spectra at levels consistent with typical comets. But scientists wanted more detailed information. They wanted to measure isotopic ratios, comparing the abundances of different isotopes of key elements. Isotopes are versions of an element with different numbers of neutrons in their nuclei. For example, most hydrogen is protium, with just a proton in the nucleus. But about 1 in every 6,000 hydrogen atoms is deuterium, with a proton and a neutron. The ratio of deuterium to hydrogen can vary depending on the conditions under which water ice formed. In the cold outer regions of a protoplanetary disk where comets form, certain chemical reactions preferentially incorporate deuterium over hydrogen. The colder the environment, the more deuterium gets incorporated. So measuring the deuterium to hydrogen ratio in a comet's water tells you something about the temperature conditions during its formation. If 3I/ATLAS had a very different ratio than solar system comets, that would indicate it formed in a significantly different environment. Measuring isotopic ratios from Earth-based spectroscopy is challenging. The signals are faint, and distinguishing between different isotopic versions of molecules requires high spectral resolution and long exposure times. For 3I/ATLAS, some teams attempted these measurements but reported results with large uncertainties. The deuterium to hydrogen ratio, if their measurements were correct, seemed broadly consistent with solar system comets, but the error bars were large enough that significant differences couldn't be ruled out. Similar attempts to measure carbon and nitrogen isotopes yielded ambiguous results. Some papers reported slight enrichments or depletions compared to solar abundances, but other papers found values consistent with solar system objects within the measurement uncertainties. Without more sensitive instruments or closer observations, definitively characterizing 3I/ATLAS's isotopic composition remained elusive. The dust composition was another area of interest. As mentioned earlier, the colour observation suggested the dust might be rich in organic material. But what kind of organics? Simple molecules like methane and formaldehyde, or complex tar-like substances, or even amino acids and other prebiotic molecules. Comets from our solar system are known to contain a rich inventory of organic compounds, some of which are the building blocks of life. If 3I/ATLAS also contained such molecules, it would indicate that the chemistry producing these compounds is universal, occurring wherever ice and carbon come together in protoplanetary disks. Some researchers analyse the infrared emission from the Coma, looking for the characteristic signatures of silicate minerals and organic compounds. Infrared spectroscopy can identify the types of bonds present in molecules based on the wavelengths of light they absorb or emit. For 3I/ATLAS, the infrared data showed features consistent with silicate dust, the silicon-oxygen minerals common in rocky material mixed with some organic compounds. Again, this was similar to solar system comets. The lack of dramatic differences in composition between 3I/ATLAS and solar system comets was itself informative. It suggested that the basic processes of planet formation, the condensation of ices and dust in cold protoplanetary disks, are similar across different stellar systems. The star where 3I/ATLAS formed might have been a different spectral type than the Sun, perhaps hotter or cooler, but the overall chemistry in the outer regions of its planetary disk was apparently similar enough to produce a comet that looks like ours. This makes sense given what we know about stellar and planetary formation. The raw materials, hydrogen, helium, carbon, oxygen, and heavier elements, are produced by stars and scattered through the galaxy by supernova explosions. When new stars form from collapsing clouds of interstellar gas, they incorporate these elements, and the mix is fairly consistent across the galaxy. Some variation occurs. Stars near the galactic centre have slightly more heavy elements than stars in the outer disk, but overall the chemistry is universal. Still, scientists hoped for at least some clear difference that would mark 3I/ATLAS as definitively from elsewhere. A unique isotopic signature, a rare mineral, an unusual ratio of elements, something that could serve as a fingerprint of its alien origin. The lack of such a smoking gun was slightly disappointing from a scientific perspective, though it did reinforce the idea that planetary systems throughout the galaxy are more similar than different. One intriguing possibility that some researchers speculated about was whether 3I/ATLAS could have formed not around a main sequence star like the Sun, but around a different type of object, perhaps a brown dwarf or a white dwarf. These objects have very different conditions in their environments, and the chemistry of planet formation around them could be different. But there was no evidence to support this idea for 3I/ATLAS. It was just one of many speculative thoughts that come up when scientists are trying to understand an unusual object. The composition studies, while not providing definitive answers, contributed to a growing picture of 3I/ATLAS as an object that was broadly similar to solar system comets, but with enough unusual characteristics to keep researchers intrigued. It was natural, almost certainly, but perhaps not typical. And that's interesting in its own way. To make sense of all the observations, many research teams turn to computer models, simulating how a comet should behave under various assumptions, and comparing the results to what was actually observed. These models are essential tools in modern astronomy, allowing scientists to test ideas that would be impossible to explore through direct experimentation. Let's consider what the models revealed. The simplest models treated 3I/ATLAS as a spherical nucleus of pure ice sublimating uniformly as it warmed. You input the comet's size, distance from the Sun, and assumed composition, and the model calculates how much gas should be produced, how large the coma should be, and how the outgassing thrust should affect the orbit. These simple models are useful as baselines, showing what you'd expect for an idealized comet. When researchers ran these models for 3I/ATLAS, they found discrepancies with the observations. The predicted gas production was higher than what was measured spectroscopically, and the predicted brightness from dust was lower than observed. This confirmed quantitatively what was apparent qualitatively. 3I/ATLAS didn't behave like a simple idealized comet. So the models were made more sophisticated. Researchers added complexities like an irregular nucleus shape, which changes how sunlight heats different parts of the surface and can create uneven outgassing. They included models of how dust is lifted from the surface, accounting for the fact that larger dust grains require more gas flow to be lofted than smaller ones. They simulated thermal inertia, the property of materials that determines how quickly they heat up and cool down, which affects when and where outgassing occurs most vigorously. Some models explored the effects of a non-uniform surface composition. Perhaps parts of the nucleus were covered with a dusty crust that insulated the ice beneath, while other parts had exposed ice sublimating freely. This could create localized jets of gas rather than uniform outgassing, and jets can produce different dust-to-gas ratios depending on their strength and the properties of the surface material being eroded. Fragmentation was also modelled. Researchers simulated what would happen if the nucleus split into two or more pieces at various points during its approach. They calculated how the fragments would separate, how the total surface area available for outgassing would change, and how the observed brightness and coma would evolve. Some of these fragmentation models could reproduce aspects of the observations reasonably well, though they required specific assumptions about when and how the fragmentation occurred. Another class of models explored the possibility of unusual dust properties. What if the dust grains in 3I/ATLAS were systematically different from typical comet dust? Perhaps more reflective or differently shaped. By adjusting the optical properties of the dust in the models, researchers could sometimes match the observed brightness with lower gas production rates. But this just moved the question to why the dust would be different, which still required explanation. More exotic models considered whether the nucleus might have contained materials that don't exist in solar system comets. Perhaps compounds that form only at very low temperatures, or that are produced by different chemical pathways. These models were highly speculative, but they represented the kind of thinking outside the box that's sometimes necessary when conventional models fail to explain observations. One interesting result from the modelling work was that no single model could explain all the observations simultaneously. Models that matched the brightness didn't match the gas production. Models that matched the trajectory didn't match the spectroscopy. This is not uncommon in astronomy. Real objects are complex, and our models are simplifications that capture some aspects while neglecting others. But it did mean that a fully satisfactory explanation for 3I/ATLAS's behaviour remained elusive. Some researchers took a Bayesian approach, using statistical methods to compare different models and determine which were most consistent with the data given our prior knowledge about comets. These analyses typically favoured natural models involving fragmentation or unusual dust properties over artificial explanations, simply because the natural models required fewer extraordinary assumptions. But the statistical preferences weren't overwhelming, leaving room for continued debate. Computer models also helped explore what future observations might resolve the ambiguities. If you could measure the Coma's properties with higher resolution, what would you look for? If you could get closer or observe at different wavelengths, what signatures would distinguish between competing hypotheses? These exercises in planning future observations are valuable even if the specific object in question is long gone, because they prepare us for the next interstellar visitor. One consistent conclusion from the modelling work was that better data would make a huge difference. Many of the uncertainties arose from measurement limitations, observations that were close to the limits of what telescopes could detect. With better instruments, brighter objects, or closer approaches, the picture would become much clearer. This was a call to action for the astronomical community to invest in improved survey capabilities and more sensitive spectrographs. Beyond fragmentation and artificial origins, researchers proposed several other possible explanations for 3I/ATLAS's unusual characteristics. Some of these ideas were conventional, extensions of known cometary processes. Others were more speculative, invoking phenomena that hadn't been observed directly but were theoretically possible. Let's explore a few of them. One idea was that 3I/ATLAS might be a transition object between a comet and an asteroid, something that had most of its ice depleted but still retained enough to show some activity. In our solar system, there are objects called main belt comets or active asteroids that show comet-like tails despite residing in the asteroid belt. These objects apparently have pockets of ice buried beneath their surfaces, and when solar heating penetrates deep enough, the ice sublimates and creates a temporary coma. If 3I/ATLAS was such a transition object, it might have a nucleus dominated by rock and dust, with only a small fraction of ice remaining. This could explain the low gas production relative to brightness. Most of the brightness would come from reflecting sunlight off the dusty surface and dust particles already in the coma. While only limited ice sublimation occurred, the object would be mostly asteroid-like, but with just enough ice to blur the distinction. But this explanation had problems. 3I/ATLAS showed clear spectroscopic signs of molecules produced by sublimating ice, and its coma was more developed than typically seen in main belt comets. It looked more like an active comet than a barely active asteroid. Still, the transition object idea reminded researchers that nature doesn't always fit neatly into categories. Objects exist along a continuum from icy comets to rocky asteroids, and 3I/ATLAS might fall somewhere in the middle. Another hypothesis involved the comet having a highly porous or fluffy structure. If the nucleus was extremely low in density, essentially a very loosely bound aggregate of ice and dust, it might behave differently than a more compact comet. A porous structure would have a large internal surface area where ice could sublime, and the gas might diffuse through the structure rather than escape directly from the surface. This could alter the outgassing pattern and potentially the dust-to-gas ratio. Measurements of some solar system comets have revealed surprisingly low densities, in some cases less than half the density of water ice, indicating high porosity. If 3I/ATLAS were even more porous, that could contribute to its unusual properties. But without direct measurements of its mass, determining its density was impossible. Density requires knowing both the size and mass, and while the size could be estimated from brightness, the mass couldn't be measured unless the comet had a satellite or passed close enough to another body to perturb its orbit noticeably. Some researchers wondered if 3I/ATLAS might be what's called a dormant comet reactivating. A dormant comet is one that has lost most of its volatile ices through repeated solar passages, leaving a dark, inert surface. But sometimes, dormant comets can reactivate if a collision or landslide exposes fresh ice beneath the crust. If 3I/ATLAS had been dormant for a long time and was just beginning to reactivate, that could create unusual observational signatures as the newly exposed ice started sublimating. However, this explanation seemed less likely given that 3I/ATLAS was on an interstellar trajectory. For it to have been dormant, it would have needed previous close stellar passages to deplete its surface ice. But tracing its orbit backward didn't show any obvious close encounters with stars in the recent past. Perhaps it had passed near a star millions of years ago, far enough back that the uncertainties in the trajectory calculation obscured the encounter. But that was speculative. Another class of explanations involved interactions with the solar wind and interplanetary magnetic fields. The solar wind, that stream of charged particles flowing outward from the sun, can interact with cometary gas and affect how the coma develops. Magnetic fields can channel ions and create structures in the ion tail. Perhaps some aspect of these interactions was creating effects that misled our measurements, making the comet's activity appear different than it really was. But these interactions are well studied, and while they can create fascinating phenomena like disconnection events where part of the ion tail breaks off, they don't generally produce the kind of systematic discrepancies observed in 3I/ATLAS. Still, it was worth considering whether some subtle effect might be at play, especially since 3I/ATLAS was approaching from an unusual direction relative to the plane of the solar system, potentially experiencing a different magnetic environment than typical comets. One particularly interesting idea, proposed by a small group of researchers, was that 3I/ATLAS might have spent some of its journey through interstellar space inside a dense molecular cloud. Molecular clouds are regions of space where gas and dust are much denser than the average interstellar medium, dense enough that new stars form within them. If 3I/ATLAS had passed through such a cloud, it might have accumulated a thick coating of interstellar ice and dust on its surface. This coating could alter the comet's appearance and behaviour. The interstellar material might have different composition than the original nucleus, creating a layered structure. As the comet warmed in the inner solar system, this outer layer would sublimate first, potentially producing the observed coma, while the original nucleus remained deeper inside, not yet fully activated. This could explain the unusual dust-to-gas ratio if the interstellar coating was dust-rich. The molecular cloud hypothesis was appealing because it invoked only known phenomena. Clouds exist and comets passing through them would accumulate material, but it was also difficult to test. Determining whether 3I/ATLAS had passed through such a cloud would require knowing its past trajectory with great precision, and the uncertainties were too large to say definitively. Each of these alternative explanations had strengths and weaknesses. None perfectly explained all the observations without requiring some special conditions or assumptions. This is perhaps the most honest assessment we can give. 3I/ATLAS presented a puzzle that our current understanding and data cannot fully solve. It will likely take more interstellar visitors, better observations, and perhaps new theoretical insights before we can look back and say with confidence what 3I/ATLAS really was. To appreciate the journey that 3I/ATLAS undertook before arriving at our solar system, it helps to contemplate what interstellar space is actually like. It's a realm so different from our experience, so empty and cold and vast, that the mind struggles to fully grasp it. But let's try to picture this environment where objects like 3I/ATLAS spend the overwhelming majority of their existence. Between the stars, the density of matter is extraordinarily low. In a typical region of the interstellar medium, there might be 1 atom per cubic centimetre. That's a density millions of billions of times lower than Earth's atmosphere at sea level. For comparison, the best vacuum chambers we can create on Earth are vastly denser than interstellar space. To experience something similar, you'd need to be in a volume the size of a building with just a single atom inside. The temperature, if we can call it that, is also extreme. Far from any star, the only source of heat is the cosmic microwave background radiation, that faint glow left over from the Big Bang. This radiation has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. Any object in interstellar space will eventually cool to approximately this temperature, its molecules barely moving, frozen in a deep stillness that's maintained for millions or billions of years. In such conditions, chemical processes essentially stop. There's no liquid water, no atmosphere, no weather. A comet in interstellar space is simply a cold rock of frozen gases, completely inert, travelling in whatever direction it was launched when it left its home system. It doesn't change, doesn't erode, doesn't age in the way objects on Earth do. It just exists moving through the darkness, a silent witness to the slow rotation of the galaxy. But interstellar space isn't completely empty. Besides the sparse gas, there's dust, particles of rock and ice just micrometers across. There are cosmic rays, high-energy particles, mostly protons, accelerated to nearly the speed of light by supernova explosions and other violent events. These cosmic rays bombard any object travelling through space, gradually altering the chemistry of its surface over eons. They break apart molecules, create new compounds, and darken organic material through radiolysis. There are also magnetic fields threading through interstellar space, created by currents in the tenuous gas and amplified by the galaxy's rotation. These fields are weak, much weaker than Earth's magnetic field, but they extend over vast distances and can affect the motion of charged particles. They create structure in the interstellar medium, helping to organize it into filaments and bubbles. Occasionally, interstellar space is punctuated by denser regions. Molecular clouds, as mentioned earlier, are vast accumulations of gas and dust, cold and dark, where star formation occurs. These clouds can be hundreds of light years across and contain enough material to form thousands of stars. An object passing through such a cloud would experience higher densities, perhaps 1,000 or even 1 million atoms per cubic centimetre, still incredibly empty by Earth standards, but much denser than the typical interstellar medium. For a comet travelling through interstellar space, the journey is one of profound isolation. The nearest star might be several light years away, its light so faint that it would barely be distinguishable from the other stars in the sky. There's no sense of motion because there are no nearby reference points. The comet simply exists in the darkness, its trajectory set by the forces that ejected it from its birth system, unchanging except for the extremely gradual effects of cosmic rays and the even more gradual drift caused by gravitational interactions with the galaxy itself. Light years are hard to comprehend. A light year is about 9.5 trillion kilometres. The distance light travels in 1 year. The nearest star to our Sun, Proxima Centauri, is about 4.2 light years away. That means that travelling at the speed of the fastest spacecraft humans have ever built, it would take tens of thousands of years to reach even our closest stellar neighbour. For 3I/ATLAS, moving at 31 kilometres per second relative to the Sun, it would take tens of millions of years to travel even 10 light years. During this immense journey, the comet would be completely dark. The only light reaching it would be the faint starlight from the galaxy, barely enough to see if you were standing on its surface. The Sun, from even a few light years away, would be just another star in the sky, indistinguishable except by careful measurement. The comet would be utterly alone, cold, dark, and silent, drifting through the galaxy on a path determined by ancient forces. And yet, despite this isolation, the comet is part of something larger. It's part of the galaxy's ecosystem, a piece of the material that cycles through generations of stars and planetary systems. The atoms in the comet were forged in stellar furnaces billions of years ago. They were blown into space by dying stars, drifted through the interstellar medium, and eventually collected into a new protoplanetary disk where they condensed into ice and rock. Now, ejected again, they're making another circuit, perhaps to eventually be incorporated into yet another star system in the distant future. This perspective, contemplating the vast scales of space and time involved, helps us appreciate what 3I/ATLAS represents. It's not just an interesting astronomical object. It's a messenger from another world, a sample of matter that has travelled across the galaxy, carrying information about processes and places we may never visit directly. To understand where interstellar objects like 3I/ATLAS come from, we need to understand how planetary systems form and how material gets ejected during that process. Planet formation is messy and violent, and it's during this chaos that countless objects are flung into interstellar space. Let's explore how this happens. Planetary systems begin as protoplanetary disks, vast rotating disks of gas and dust surrounding newly formed stars. These disks contain all the material that will eventually form planets, moons, asteroids, and comets. In the inner regions, close to the star where it's hot, only rocky materials and metals can condense from the gas. Further out, beyond what's called the snow line, it's cold enough for ice to exist. and the solid material available for planet building dramatically increases. Small particles of ice and dust stick together through collisions, gradually building larger objects called planetesimals, which might be anywhere from a kilometre to hundreds of kilometres across. These planetesimals continue colliding and merging, forming even larger bodies called protoplanets. Eventually, if a protoplanet grows large enough, it can gravitationally attract gas from the surrounding disk, forming a giant planet like Jupiter or Saturn. But this process isn't smooth. Protoplanets and planetesimals don't orbit in isolation. Their gravitational fields interact, perturbing each other's orbits. Large protoplanets can migrate inward or outward through the disk, pushed by gravitational interactions with the gas. As they migrate, they scatter smaller bodies, flinging them into eccentric orbits, or even ejecting them from the system entirely. Jupiter, in particular, plays a major role in our own solar system's history. Simulations suggest that Jupiter migrated inward early in the solar system's formation, moving closer to the Sun before being pulled back outward by Saturn's gravity. This grand tack, as it's called, would have scattered enormous numbers of planetesimals and protoplanets. Some crashed into the Sun, some were thrown into the outer solar system populating the Kuiper belt and Oort cloud, and some achieved escape velocity, leaving the solar system entirely to become interstellar wanderers. The violence of this process is hard to overstate. Collisions shattered larger bodies into fragments. Close encounters between planets and planetesimals flung objects in all directions at high speeds. The early solar system was a shooting gallery, with material constantly being redistributed, accreted, or ejected. And this wasn't unique to our system. Every planetary system goes through similar dynamics, though the details vary depending on the sizes and positions of the planets that form. Computer simulations of planet formation consistently show that most systems eject far more mass than they retain. For every Jupiter that forms, perhaps several Earth masses of material get thrown out of the system. Multiply that by the billions of planetary systems that have formed in the galaxy over its history, and you get an enormous population of interstellar objects, comets, asteroids, and perhaps even larger bodies drifting between the stars. Some of these ejected objects are pristine, having formed in the outer reaches of their protoplanetary disks and been ejected before they ever experienced significant heating. Others, like 3I/ATLAS might be, could have orbited closer to their star for a time, developing an outer crust before being ejected. Still others might be fragments from collisions, pieces of larger bodies shattered during the chaotic assembly of planets. The ejection process itself is worth considering. For an object to escape a solar system, it needs to reach escape velocity, the speed at which it's no longer gravitationally bound. For our solar system, escape velocity from the vicinity of Jupiter's orbit is about 18 kilometers per second relative to the Sun. An object moving faster than this will escape, while one moving slower will remain bound. Gravitational assists from planets can provide this speed. When a small object passes close to a massive planet, it can exchange energy and momentum with the planet. If the geometry is right, the object can be accelerated to escape velocity. From the planet's perspective, it barely notices the interaction. Its massive inertia means the small object has negligible effect on its motion. But from the small object's perspective, it's been flung away at tremendous speed, sent on a trajectory out of the system. This process is still happening in our solar system today, though at a much reduced rate compared to the early chaotic period. Comets from the Oort cloud occasionally fall inward, and some of them interact with Jupiter or another planet in a way that ejects them. But the rate is much lower now, perhaps one object ejected every few million years, compared to the torrents of material flung out during the formation epoch. For 3I/ATLAS, we don't know the details of its ejection. We don't know what kind of star it formed around, whether that star had planets, or what specific gravitational interactions launched it into space. But we can be fairly confident that it was ejected during the formation of its home system, billions of years ago and has been travelling through the galaxy ever since, waiting for a chance encounter with another star to briefly illuminate its existence. One of the underlying motivations for studying interstellar objects like 3I/ATLAS is the possibility, however remote, that they could carry information about life elsewhere in the galaxy. This isn't about expecting 3I/ATLAS itself to be alive or to show signs of biology. Rather, it's about what such objects could potentially tell us about the conditions for life in other planetary systems. Let's explore this fascinating angle. Life as we know it requires several ingredients: liquid water, a source of energy, and organic molecules. Comets contain water ice and organic compounds in abundance. While the water is frozen solid in the deep cold of space, and the organics are inert, these are the raw materials from which life could arise given the right conditions. If comets are common around other stars, and if the chemistry producing these ingredients is universal, then the building blocks for life are widespread throughout the galaxy. Some scientists have even proposed a hypothesis called panspermia, the idea that life might spread between star systems via interstellar objects. If life arose on a planet around one star, and if that planet experienced large impacts that ejected material into space, some of that material might contain microorganisms. These organisms would be frozen and dormant during the long journey through interstellar space. But if they eventually landed on another planet with suitable conditions, they might revive and seed life there. This idea is controversial. Most scientists think that life more likely arises independently on each planet where conditions are right, rather than being transported between stars. The journey is long, the radiation exposure is intense, and the odds of a particular ejected fragment reaching another habitable planet are vanishingly small, but it's not impossible. And some researchers continue to investigate whether hardy microorganisms could survive such a journey. For 3I/ATLAS specifically, there was no expectation of detecting life or even biosignatures. The spectroscopy showed molecules produced by non-biological processes, the same chemistry seen in solar system comets. But the fact that 3I/ATLAS contained organic compounds, assuming it's a natural comet, reinforces the idea that organic chemistry is ubiquitous. Wherever there are protoplanetary disks, there will be comets containing the precursors to life. Another aspect of the life question relates to technological civilizations. If intelligent life is common in the galaxy, and if such civilizations engage in space exploration and industry, they might leave detectable traces. Artificial satellites, probes sent to other star systems, debris from megastructure construction projects, all of these could eventually escape into interstellar space and become detectable to civilizations like ours that are starting to survey the sky for interstellar objects. This is part of the motivation behind considering artificial explanations for anomalous objects like Oumuamua and 3I/ATLAS. It's not that astronomers expect most interstellar visitors to be artificial, but if even a tiny fraction were, detecting one would be profoundly significant. It would prove that we're not alone, that other technological species exist or existed in the galaxy, and it would provide direct evidence of their capabilities and perhaps their intentions. The challenge is distinguishing artificial from natural. Nature is remarkably creative, producing objects and phenomena that can appear designed even though they arose from purely physical processes. We've been fooled before. Pulsars, when first discovered, were so regular that they were jokingly called LGMS, little green men, before we realised they were rapidly rotating neutron stars. Quasars seemed impossibly energetic until we understood they were powered by supermassive black holes. So any claim that an object is artificial requires extraordinary caution. You must rule out all plausible natural explanations first, and even then, you should probably gather more evidence before making definitive statements. For 3I/ATLAS, the artificial hypothesis remains in the realm of speculation, an idea worth mentioning but not something most scientists take seriously given the available evidence. But the search for technosignatures, as they're called, is gaining legitimacy as a scientific endeavour. Several research groups are now dedicated to searching for signs of technology from other civilizations, whether radio signals, laser pulses, atmospheric pollution on exoplanets, or megastructures like Dyson spheres. Interstellar objects represent another potential avenue for detecting such signs. If we detected an interstellar object that was clearly artificial, perhaps moving under power or transmitting signals, it would raise profound questions. Who built it? When? For what purpose? Is the civilization that built it still around? Might they be monitoring us, or have they long since vanished, leaving only their scattered creations drifting through the galaxy? These questions touch on deep issues about our place in the cosmos and our potential future, for now. We don't have answers. 3I/ATLAS likely doesn't provide them either, but every interstellar visitor is an opportunity, a chance to learn something new about what exists beyond our solar neighbourhood, and each object we study, even if it's entirely natural, adds to our understanding of the galaxy's composition, the diversity of planetary systems, and indirectly, the possibilities for life elsewhere. The study of 3I/ATLAS and Oumuamua highlighted a fundamental limitation. Observing from Earth, we can only learn so much. To truly understand interstellar objects, we need to visit them, to send spacecraft that can examine them up close, analyse their composition directly, and perhaps even return samples to Earth. Let's explore what future missions to interstellar visitors might look like and what challenges they face. The first and most obvious challenge is timing. Interstellar objects move quickly and are visible for only a limited time. To intercept one, you need to detect it early, while it's still far from the Sun, and you have time to launch and manoeuvre a spacecraft to match its trajectory. This requires survey telescopes sensitive enough to detect faint objects at great distances, and it requires rapid response capabilities to design, build, and launch a mission on short notice. Current space missions are typically planned years or even decades in advance. Building a spacecraft, testing it, and preparing it for launch is a lengthy process. But for an interstellar object, you might have only a few months' warning. This mismatch has led to proposals for rapid response missions that could be launched quickly when a suitable target is detected. One concept is to maintain a spacecraft in a state of readiness, pre-built and pre-tested, waiting for a target to appear. When an interstellar object is detected, the spacecraft could be quickly prepared for launch, with a mission trajectory calculated and uploaded just days before liftoff. This approach requires investment to build and maintain the standby spacecraft, but it would dramatically increase our chances of successfully intercepting an interstellar visitor. Another approach is to develop very fast propulsion systems that could catch up to an interstellar object even if launched after the object has been detected. Chemical rockets, the current standard for space travel, are too slow. Even the fastest spacecraft we've launched, like the Parker Solar Probe, would struggle to overtake an object moving at 30 or 40 kilometers per second relative to the Sun unless it had years of warning. Nuclear propulsion, however, could change the equation. A spacecraft powered by nuclear thermal or nuclear electric propulsion could achieve much higher velocities, potentially reaching speeds of 50 to 100 kilometers per second or more. Such a spacecraft could intercept an interstellar object even with relatively short notice, catching up during its passage through the inner solar system. There have been serious proposals for such missions. In the wake of Oumuamua's detection, several groups designed conceptual missions to intercept similar objects. One European study looked at using solar sails combined with laser propulsion to rapidly accelerate a lightweight probe. Another American study examined a nuclear-powered spacecraft that could launch within months of an object's discovery and reach it within a few years. These missions face significant technical challenges. Spacecraft moving at such high speeds experience enormous heating from friction with the sparse interstellar medium and from high-energy particle impacts. They need robust shielding and cooling systems. navigation is also challenging. You need to know the target's trajectory extremely precisely to ensure an intercept, and any error could cause the spacecraft to miss by thousands of kilometers. If a mission did successfully reach an interstellar object, what would it do? The most basic goal would be imaging, cameras capturing detailed pictures of the object's surface, revealing its shape, texture, any features like craters or cracks. This alone would be invaluable, providing direct evidence of the object's nature and history. Spectroscopy from close range would be next. Instruments could analyze the composition of the surface and any coma with far greater precision than Earth-based observations allow. You could definitively determine isotopic ratios, identify specific minerals and organic compounds, and map composition variations across the surface. Some mission concepts include landers or impactors. A small probe could touch down on the object's surface, drill or scrape a sample, and analyze it with onboard instruments. Or the spacecraft could release an impactor that crashes into the object at high speed, creating a plume of ejected material that the main spacecraft flies through and analyzes. This is similar to what NASA's Deep Impact mission did with Comet Tempel 1 in 2005. The ultimate goal would be a sample return mission, collecting material from an interstellar object and bringing it back to Earth. Laboratories on Earth can analyze samples with far greater sophistication than any spacecraft instrument, revealing details about formation conditions, chemical history, and potentially even whether the object ever experienced biological processes. But sample return is extremely challenging, requiring the spacecraft to rendezvous with the object, collect material, and then return to Earth, all while moving at high interstellar velocities. Despite these challenges, the scientific community is increasingly recognizing the importance of interstellar object missions. As survey capabilities improve and we detect more such objects, the case for dedicating resources to exploring them strengthens. Some researchers argue that intercepting an interstellar visitor should be a high priority for space agencies, comparable to exploring Mars or returning samples from asteroids. There's also the possibility of lucky timing. If an interstellar object happened to pass very close to Earth, within a few million kilometers, existing spacecraft or even hastily launched probes could reach it with conventional propulsion. This would be extremely fortunate, but given that we're now detecting these objects more regularly, it's not impossible that such an opportunity might arise within the next few decades. For now, we rely on remote observation. Telescopes on Earth and in space watching as these visitors sweep through our neighborhood and depart. But the future may hold closer encounters, missions that transform interstellar objects from distant points of light into places we've visited, touched, and sampled. As observations of 3I/ATLAS wound down in early 2020, as the comet faded from view and disappeared back into the darkness of interstellar space, researchers began compiling their findings and reflecting on what had been learned. It's worth taking stock of the scientific legacy of this brief visitor and what it taught us about the universe beyond our solar system. First, and most fundamentally, 3I/ATLAS confirmed that interstellar objects do pass through our solar system regularly enough to be detected with current technology. 2 confirmed interstellar visitors in just over 2 years suggested a population that could be sampled and studied. This was a transition from purely theoretical discussions about interstellar material to having actual examples to examine. Second, 3I/ATLAS demonstrated that interstellar comets can appear broadly similar to solar system comets in many respects. It had a coma, a tail, spectroscopic signatures of water and organic compounds, and behavior consistent with sublimating ice. This similarity implied that the basic processes of comet formation, the condensation of ice in cold protoplanetary disks, operate similarly around different stars. The universe, at least in this respect, shows remarkable uniformity. Third, and perhaps most intriguingly, 3I/ATLAS showed that interstellar objects can also have subtle differences that challenge our understanding. The unusual dust-to-gas ratio, the peculiar brightness relative to gas production, the weak non-gravitational acceleration, these weren't explained away by simple models. They suggested that either interstellar comets have properties we don't fully understand, or that 3I/ATLAS was somehow special, perhaps fragmenting or having an unusual history. These anomalies sparked productive scientific debate. Papers were published proposing and testing different hypotheses. Researchers refined their models of cometary activity and thought more carefully about what assumptions were justified. This is how science progresses. Not through easy answers, but through puzzles that force deeper thinking. 3I/ATLAS also contributed to the growing realization that the interstellar medium is more accessible to study than previously thought. We don't have to send spacecraft across light years to sample material from other star systems. The material comes to us, if we're patient and attentive. Each interstellar visitor is a free sample delivery, bringing information about distant planetary systems right to our cosmic doorstep. In terms of specific discoveries, 3I/ATLAS added to our knowledge of comet compositions and behaviours. Even if it was just a normal comet from elsewhere, that quote 3 comet provided a data point from a different formation environment. Over time, as we accumulate data from dozens or hundreds of interstellar visitors, patterns will emerge. We'll learn how comet properties vary with the type of star they formed around, the age of their home systems, and their histories during ejection and interstellar travel. The object also served as a reminder of the importance of international collaboration in astronomy. Observations of 3I/ATLAS came from telescopes around the world, from professional observatories and amateur astronomers alike. Data was shared openly, and research groups analysed and cross-checked each other's findings. This collaborative spirit is one of the great strengths of the astronomical community, and it was fully on display in the study of this transient visitor. On a more speculative level, 3I/ATLAS contributed to discussions about technosignatures and the search for evidence of other civilizations. While the object almost certainly was natural, the fact that its properties generated debate about artificial possibilities highlighted the need for clear criteria to distinguish natural from artificial. This work will be important as we continue to detect interstellar objects and want to ensure we don't miss a genuinely artificial one if it appears. The object also raised practical questions about planetary defense. If interstellar objects pass through the solar system regularly, is there any chance one could collide with Earth? The answer is that the risk is extremely low. Space is vast, Earth is a tiny target, and even though interstellar objects move fast, their trajectories can be predicted accurately enough to rule out impacts years in advance. Still, it's worth monitoring such objects carefully, and 3I/ATLAS provided practice for tracking fast-moving targets. Perhaps most importantly, 3I/ATLAS inspired wonder. For a few months, people around the world could contemplate an object that had travelled from another star system, a visitor from the vast spaces between suns. News articles described it, enthusiasts discussed it on forums and social media, and educators used it to teach students about the solar system and galaxy. This public engagement is valuable, reminding us that exploration and discovery aren't just for scientists, but for everyone who looks up at the night sky and wonders what's out there. As 3I/ATLAS receded into darkness, crossing the orbit of Jupiter and heading back toward the interstellar medium, it left behind a legacy of data, papers, debates, and inspiration. The story of this comet isn't fully written. Researchers will continue analysing the data for years, and future discoveries may provide context that helps interpret what 3I/ATLAS really was. But for now, we can appreciate what it gave us: a glimpse of the cosmos beyond our solar neighbourhood, a puzzle to solve and a reminder that the universe is full of mysteries waiting to be explored. The story of 3I/ATLAS raises interesting philosophical questions about evidence, certainty, and how we decide what's true. In science, we're constantly navigating between skepticism and openness, between demanding rigorous proof and remaining willing to consider new ideas. The debates about this interstellar visitor illuminate how that navigation works. Let's reflect on what constitutes good evidence and how scientists think about unusual observations. In an ideal world, evidence would be clear and unambiguous. An observation would definitively support one hypothesis and rule out all others, but reality is messier. Most observations are consistent with multiple explanations, each with different levels of plausibility. The challenge is weighing these explanations, judging which requires fewer assumptions, which is more consistent with our broader understanding of how nature works, and which makes predictions that can be tested. For 3I/ATLAS, the evidence was ambiguous. The unusual dust-to-gas ratio could be explained by fragmentation, unusual composition, measurement errors, or conceivably even artificial origins. None of these explanations was perfectly satisfying. Each required some special pleading or assumptions that couldn't be fully verified. Scientists had to make judgments about which explanation was most likely true, and those judgments involved both data and intuition informed by experience. This is where the principle of parsimony comes in, often called Occam's razor. When multiple explanations fit the observations, prefer the simplest one that requires the fewest unsupported assumptions. A fragmenting comet is simpler than an alien probe because we know comets fragment, and we've never confirmed alien technology. This doesn't mean the simpler explanation is always correct. Nature can be complex and surprising, but it's a reasonable starting point. However, parsimony must be balanced against the risk of dismissing genuinely new phenomena too quickly. History is full of examples where unusual observations that didn't fit prevailing theories were initially dismissed as errors or anomalies, only to later be recognised as evidence of something genuinely new. Pulsars, as mentioned earlier, are one example. Quasars are another. Ball lightning might be a third, long dismissed by some scientists as misidentification until better evidence accumulated. The key is to remain open while maintaining high standards for evidence. You don't reject unusual ideas out of hand, but you do require extraordinary evidence before accepting extraordinary claims. For 3I/ATLAS, the claim that it might be artificial is extraordinary, so the evidence threshold is high. The actual evidence falls well short of that threshold, so most scientists conclude it's natural, but they don't completely dismiss the possibility. They simply assign it a very low probability given current data. This Bayesian way of thinking, assigning probabilities to hypotheses and updating them as new evidence arrives, is increasingly how scientists approach ambiguous questions. Instead of saying something is definitely true or false, you say there's a certain probability it's true given what we know. As better observations or new theoretical insights emerge, those probabilities shift. For future interstellar objects, the hope is that improved data will make probabilities sharper, pushing them closer to certainty in one direction or another. Better spectroscopy might definitively show natural composition. Or alternatively, some future object might show clear signs of artificial structure, moving the probability of artificial origins for that object toward near certainty. There's also the question of how we communicate uncertainty to the public. Science journalism and public communication often struggle with this. Headlines want definitive statements, quote 4 or quote 5, but the reality is usually more like quote 6 that doesn't make for catchy headlines, but it's more honest. For 3I/ATLAS, some media reports suggested it might be an alien probe, playing up the most exotic possibility while downplaying that most scientists thought it was natural. This created false impressions and probably disappointed readers expecting dramatic revelations. Better science communication would acknowledge the mysteries while being clear about what's speculative versus what's well supported. Scientists themselves also bear responsibility for clear communication. When publishing papers exploring unusual ideas, they should be explicit about the level of speculation involved. phrases like quote 7 or quote 8 should be accompanied by honest assessments of probability. The goal is to explore ideas without overselling them, to maintain scientific rigour while encouraging creative thinking. The broader lesson from 3I/ATLAS is that science is a process of iterative refinement. We make observations, propose explanations, test predictions, gather more data, and revise our understanding. Certainty is rare. Most questions remain partially open, our answers provisional, subject to revision as knowledge improves. This isn't a weakness of science, but a strength, a willingness to change our minds when evidence demands it, to value truth over ego or dogma. Contemplating 3I/ATLAS also invites us to think about time and distance in ways that challenge our everyday intuitions. The scales involved, the millions of years and light years, are so far beyond human experience that we can state them numerically, but struggle to feel them viscerally. Yet these scales are fundamental to understanding interstellar visitors and our place in the cosmos. Let's try to build some intuition for these vast dimensions. Start with time. 3I/ATLAS likely spent millions of years, possibly hundreds of millions or even billions, travelling through interstellar space before entering our solar system. 1,000,000 years is 1,000 millennia. All of recorded human history, from the earliest writing to the present, spans only about 5 millennia. So 1,000,000 years is 200 times all of human history, and that might be the short end of how long 3I/ATLAS travelled. During that time, continents shifted on Earth. Mountain ranges rose and eroded. Species evolved and went extinct. The climate cycled through ice ages and warm periods, and through all of that, 3I/ATLAS drifted in the cold darkness, unchanging, unaware, simply existing in the space between stars. Now consider distance. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. That's about 40 trillion kilometres. If you could drive a car at highway speed toward Proxima Centauri, it would take more than 40 million years to arrive. Even travelling at the speed of the fastest spacecraft we've built, it would take tens of thousands of years. The distances are so immense that conventional propulsion becomes almost meaningless for interstellar travel. 3I/ATLAS travelled perhaps dozens or hundreds of light-years during its journey. At its speed of 31 kilometers per second, it covers about 1 light-year every 10,000 years. So if it travelled 100 light-years, that journey took about 1,000,000 years. If it travelled farther, the timescale extends proportionally. Every additional light-year is another 10 millennia of travel through the void. These numbers become abstract, losing their emotional weight. How do we make them meaningful? One way is to relate them to things we do understand. 1,000,000 years ago, our ancestors were Homo erectus. Not yet fully modern humans. They were just learning to control fire and craft more sophisticated stone tools. The entire arc of human civilization, from those early toolmakers to the present day, is shorter than the likely travel time of 3I/ATLAS. Another way to grasp these scales is to think about what changes over such spans. Stars move through the galaxy, orbiting the galactic centre. Our Sun completes one orbit every 230 million years, so if 3I/ATLAS has been travelling for hundreds of millions of years, it and our Sun have both completed substantial fractions of galactic orbits, moving through different regions of the Milky Way during that time. Galaxies themselves evolve. 200 million years ago, when dinosaurs walked the Earth, the Milky Way had a slightly different structure than today. Stars have been born and died, enriching the interstellar medium with heavier elements. The average composition of gas in the galaxy has shifted subtly, and through all of that cosmic evolution, objects like 3I/ATLAS have been travelling, silent witnesses to the slow changes in the galactic environment. There's a profound loneliness in contemplating these journeys. Imagine being an object adrift in interstellar space. No nearby stars, no planets, no other objects visible except as distant pinpoints of light. No change, no events, no milestones except perhaps the occasional distant passage near a star every few million years. Just existence, unchanging existence, for eons beyond comprehension. And yet, there's also a kind of peace in it. No storms, no quakes, no threats. Just stillness and cold and darkness. If consciousness were possible for such an object, would it experience time at all? Would millions of years feel like anything when nothing ever happens? These questions verge on philosophy rather than astronomy, but they're worth pondering. When 3I/ATLAS finally entered our solar system, it was a brief interruption in this vast journey. A few months of warmth and light and change, a period of activity as the sun's heat energized its frozen surface, and then departure back into the cold, back to the long silence that will likely continue for millions or billions more years, until perhaps, by chance, it enters another stellar system, or by even longer odds, collides with some other object and ends its journey. This perspective makes our own lives seem fleeting. We measure our existence in decades, maybe a century if we're fortunate. Against the timescales of interstellar voyages, a human lifetime is less than the blink of an eye. Everything we do, all of our concerns and achievements and struggles, occupies a vanishingly thin slice of cosmic time. But perhaps that's not depressing. Perhaps it's liberating. If the universe operates on such vast scales, then our individual worries are placed in perspective. The stress of daily life, the anxieties about the future, they matter to us personally, but against the backdrop of cosmic time and space, they're whispers in infinity. This doesn't mean they don't matter at all. They matter to us, and to those we affect. But it does suggest a certain acceptance, a recognition that we're part of something far larger than ourselves. One of the deeper questions that interstellar objects like 3I/ATLAS touches on is the Fermi paradox, the puzzle of why. If the universe is so vast and old, we haven't detected clear evidence of other technological civilizations. If intelligent life is common, and if such life often develops technology and explores space, shouldn't we see signs of them? Shouldn't we have detected radio signals, seen megastructures, or found clear artifacts? The fact that we haven't is sometimes called the Great Silence. Let's contemplate what this might mean. There are many proposed solutions to the Fermi paradox. Perhaps life is rare, requiring such specific conditions that even in a galaxy with hundreds of billions of stars, technological civilizations are few and far between, space so far apart that contact is unlikely. Perhaps intelligence is common, but technology is rare, requiring specific evolutionary paths or cultural developments that don't often occur. Perhaps civilizations self-destruct, destroying themselves with nuclear weapons or environmental collapse before they can spread to the stars. Or perhaps civilizations do spread but remain undetectable. Maybe they use communication methods we haven't discovered yet, or they deliberately avoid contact with younger civilizations like ours. Maybe they've transitioned to forms of existence we wouldn't recognize, uploading their minds to computers or transforming into something so different from biological life that we wouldn't know where to look. Interstellar objects add an interesting dimension to this discussion. If technological civilizations build spacecraft and probes and launch them into the galaxy, those objects should eventually become part of the interstellar population. Over millions of years they'd accumulate scattered throughout the galaxy alongside natural asteroids and comets. If civilizations are common and long-lived, the ratio of artificial to natural interstellar objects might be measurable. So far we haven't definitively identified any artificial interstellar objects. Out of 2 confirmed interstellar visitors, neither shows clear signs of technology despite some unusual properties. If we extrapolate, if most interstellar objects turn out to be natural even with much better observations, that tells us something. Either technological civilizations are rare, or they don't prolifically send probes into space, or their probes are designed to be indistinguishable from natural objects. That last possibility is intriguing. If you were designing an interstellar probe for a mission lasting millions of years, you might deliberately make it look natural to avoid detection by other species. Camouflage could be a strategy for avoiding unwanted attention or conflict. So even if artificial objects exist among the interstellar population, they might be hard to identify without getting very close and examining them in detail. But this reasoning can become unfalsifiable. If you don't see artificial objects, you can always claim they're just well disguised. Science works best when hypotheses make predictions that can be tested and potentially falsified. The claim that interstellar probes exist but are perfectly camouflaged is hard to test, which makes it unsatisfying scientifically even if it's possible. Perhaps the simplest explanation for the Great Silence is that technological civilizations are genuinely rare. The conditions for life might be common. Simple microbes might exist on many worlds, but the development of intelligence and technology might require such an unlikely sequence of events that it occurs only a handful of times per galaxy. If that's the case, the nearest other civilization could be tens of thousands of light years away, too distant for meaningful contact or even mutual detection. There's also the timescale issue. Civilizations might be common but exist at different times. If a typical technological civilization lasts 100,000 years, a blink in cosmic time, then civilizations would rarely overlap. One might arise, flourish, and vanish before the next emerges. They'd be scattered through time as well as space, never coexisting in a way that allows contact. Contemplating these possibilities can feel lonely. The idea that we might be alone, or functionally alone because other civilizations are too distant or temporally separated, is profound. It suggests that the responsibility for understanding and caring for the universe falls on us, at least in our corner of the galaxy. There's no one to guide us. No older civilization to teach us or rescue us from our mistakes. We're on our own. But there's also something hopeful in this. If civilizations are rare, then each one is precious, an unlikely emergence of complexity and consciousness in a mostly inert universe. Our existence matters not because we're common, but because we're rare. And if we are alone, or nearly so, then the exploration of the cosmos becomes even more important. We're the universe's way of knowing itself, the witnesses to its beauty and mystery. Interstellar objects like 3I/ATLAS, whether natural or artificial, are messengers from that vast cosmos. Each one that passes through our solar system is a reminder that we're connected to something larger, that the space between stars isn't empty, but filled with material that travels and eventually interacts. Every detection is an opportunity to learn, and every mystery we uncover brings us slightly closer to understanding our place in the cosmic story. Throughout this exploration of 3I/ATLAS, a theme that keeps emerging is human curiosity, our desire to understand, to explore, to ask questions, even when answers are uncertain. This curiosity is one of our defining characteristics as a species, and it's worth reflecting on why we care about distant comets and the space between stars. What drives us to invest time and resources in studying these fleeting visitors? Part of it is practical. Understanding the composition and frequency of interstellar objects helps us understand the galaxy's structure and history. It informs our models of planetary formation and might someday provide resources if we develop the capability to mine asteroids, including interstellar ones. There's also the planetary defense angle, making sure we can track anything that might pose a collision risk. But most of the motivation is less practical and more fundamental. We want to know because we're curious. We want to understand how the universe works, what's out there, where we fit in the cosmic order. These questions don't have immediate practical applications, but they speak to something deep in human nature, a drive to explore and comprehend that seems almost as fundamental as our needs for food and shelter. This curiosity has driven every major exploration in human history. Early humans spreading across continents into unknown territories. Polynesian voyagers crossing vast expanses of ocean to find new islands, European explorers circling the globe, the space race pushing us to the moon, and now robotic missions exploring the solar system and telescopes peering into the depths of space and time. Each of these explorations expanded our understanding and changed how we see ourselves. The voyages of discovery revealed that Earth is round, a sphere floating in space, not a flat expanse with edges. The Copernican revolution showed that Earth orbits the Sun, not the other way around, displacing us from the centre of creation. The discovery of the vastness of the universe, billions of galaxies each containing billions of stars, further diminished our cosmic significance while simultaneously revealing the majesty of the cosmos we're part of. Interstellar objects continue this tradition. They're reminders that our solar system is just one among countless others, that the material we're made of is not unique to Earth, or even to our stellar neighbourhood. The atoms in your body were forged in ancient stars, scattered through space by supernova explosions, collected into the cloud that formed our sun and planets, and now temporarily organised into the pattern that is you. In a very real sense, you are made of stardust, and so is 3I/ATLAS. This connection between us and the cosmos can inspire wonder, that emotion we feel when confronted with something vast and beautiful that we don't fully understand. Wonder is related to curiosity but tinged with awe, a recognition that the universe is grander and more mysterious than we imagined. It's the feeling you get looking up at a clear night sky and seeing the Milky Way stretched across the darkness, or contemplating the fact that light from distant galaxies has been travelling for billions of years to reach your eyes. Science, at its best, cultivates wonder while also seeking to understand. These aren't opposed goals. Understanding doesn't diminish wonder, it often enhances it. Knowing that the light you see from a distant star left that star hundreds or thousands of years ago, that you're looking backward in time, makes the experience richer, not less magical. 3I/ATLAS in its brief visit offered a moment of wonder. For a few months we could point telescopes at an object that had come from another star system, travelled for eons through the void, and happened to pass through our neighbourhood. We could watch it, measure it, speculate about its origins and nature, and even though it's gone now, faded back into darkness, the wonder remains in the data and images and questions it left behind. This wonder matters because it reminds us that there's always more to discover. No matter how much we learn, the universe has more secrets. Every answer raises new questions. Every explained mystery reveals deeper mysteries behind it. This is true in every field of science, but it's especially poignant in astronomy, where the objects of study are so distant and vast that we can never fully explore them directly, only observe from afar and try to piece together their stories, and so we keep looking. We build better telescopes, more sensitive detectors, more sophisticated analysis techniques. We watch the sky for the next interstellar visitor, knowing it will come eventually, maybe next year or maybe not for a decade. But it will come, and when it does, we'll point every instrument we have at it, gathering data, asking questions, marvelling at another messenger from the vast spaces between stars. As we near the end of this exploration, let's return to 3I/ATLAS itself and imagine its continuing journey. By now, years after its passage through our solar system, it has crossed far beyond the orbit of Neptune, moving through the dim outer reaches where sunlight is so faint that the sun appears merely as a bright star among many. The comet's brief period of activity is long over. The warming that created its coma and tail has ceased, and it has returned to its frozen state, dark and silent once more. 3I/ATLAS is now truly departing, escaping the sun's gravitational influence and returning to interstellar space. This transition isn't abrupt. There's no clear boundary where the solar system ends and interstellar space begins. The Oort cloud, that vast sphere of comets surrounding the sun, at distances up to a light year or more, is still considered part of the solar system, though its outer reaches blend into the interstellar medium. The comet will pass through this region over thousands of years, gradually increasing its distance from the Sun, gradually slowing as the last traces of solar gravity tug against its outward motion. Eventually, perhaps 20 or 30,000 years from now, it will be so far that the Sun's influence is negligible. It will have returned to the interstellar medium, just another dark object among countless others drifting through the galaxy. What will happen to it next is uncertain. It might travel for millions of years without encountering anything significant, just slowly moving through the sparse gas and dust between stars. It might pass through a molecular cloud, accumulating a new coating of interstellar ice and dust. It might by chance pass relatively close to another star, perhaps experiencing another brief warming before continuing on. Or it might continue for billions of years, longer than human civilization has existed, longer than humans as a species have existed, long enough for continents to merge and separate multiple times on Earth, for new species to evolve and others to vanish, for stars to be born and die in the cosmic neighbourhood. Through all of this, 3I/ATLAS would simply exist, unchanging, unaware, a patient traveller on a journey without destination. There's something almost meditative about this perspective. The comet doesn't hurry. It doesn't worry about its trajectory or wonder about its fate. It simply is, moving through space according to the laws of physics, following the path determined by the forces that acted on it billions of years ago when it was ejected from its home system. In a strange way, we might envy that simplicity. Human life is full of anxiety and uncertainty, questions about purpose and meaning, concerns about the future. We experience time as a constant flow, always moving from past to present to future, and we're acutely aware of time's passage, of aging, of mortality. But for 3I/ATLAS, if objects could experience anything, time might not feel like flow at all. In the cold stasis of interstellar space, 1 million years is indistinguishable from the next. This reminds us that the universe operates on scales, and according to principles that are indifferent to human concerns. The cosmos doesn't care about our anxieties or ambitions. It simply is, unfolding according to the laws of physics, evolving over timescales that dwarf human comprehension. And yet, within this vast, indifferent universe, we exist. We're complex patterns of matter and energy that have somehow developed consciousness, the ability to observe and question and wonder. Our existence, however brief and small in cosmic terms, allows the universe to know itself. Through our telescopes and spectrographs, through our observations of objects like 3I/ATLAS, the universe looks at itself. We are the cosmos examining its own nature, trying to understand its origins and structure and fate. That's remarkable. That's meaningful in a way that transcends our individual lifetimes or concerns. As 3I/ATLAS continues its journey, it carries with it the information we gathered. Not literally, the data exists in computers and papers and human memories, but conceptually. It connected with our civilization, however briefly and distantly. We observed it, measured it, debated its nature. In doing so, we transformed it from an unknown object to a known one, from a mere point of light to a complex entity with a history and properties we can describe. And perhaps, millions of years from now, 3I/ATLAS will pass through another solar system, where another civilization looks up and sees it, another species of curious beings who will observe and measure and wonder. They'll have their own questions, their own theories, their own debates. Maybe they'll detect signs of our observations, spectroscopic signatures altered by our instruments, or maybe not. But they'll add their knowledge to the story of this wanderer, another chapter in a book that spans galaxies and eons. This multi-generational, multi-civilization perspective is humbling and beautiful. We're part of a cosmic community, not through direct communication or contact, but through shared participation in the universe's unfolding story. Objects like 3I/ATLAS are the threads connecting us, messengers that travel between stars, potentially observed by different civilizations separated by vast gulfs of space and time. And so we've travelled together through the story of 3I/ATLAS, from its discovery on that August night in 2019 to its departure back into the cosmic void. Over these 2.5 hours, we've explored the observations that puzzled astronomers, the hypotheses proposed to explain its unusual properties, the broader context of interstellar objects and what they might tell us about the galaxy. We've contemplated deep questions about time, distance, life, and our place in the universe. The answer to our opening question, whether 3I/ATLAS was natural or something else, is probably that it was natural. A comet from another star system. Unusual in some respects, but still explicable by known physical processes. Perhaps it was fragmenting. Perhaps it had unusual composition due to its formation environment. Perhaps it had passed through regions of space that altered its surface. We may never know for certain. But natural explanations are sufficient and most likely correct. But the question itself was valuable to ask. It pushed researchers to think carefully about what would constitute evidence for artificial origins. It sparked interesting discussions about how common technological civilizations might be and what traces they might leave. And it reminded us that the universe can surprise us. That what we think we understand might have hidden complexities. If you enjoyed this slow drift through cosmic mysteries, a like and subscribe truly helps this channel reach others seeking the same peaceful way to learn and reflect. And please share your thoughts in the comments. Where in the world are you watching from? What aspects of this story resonated with you? These conversations create a community of curious minds exploring the universe together, wherever you are right now. I hope you're comfortable. I hope your breathing has slowed and steadied through our time together. I hope the concerns of your day have receded, at least for these moments, replaced by contemplation of something vast and ancient and strange. I hope you found some peace in the questions we've explored, even without final answers. Look up at the night sky when you can, if you can. Somewhere out there, far beyond the visible stars, 3I/ATLAS continues its journey. It's too distant and faint to see, lost in the darkness between stars, but it's there, moving steadily through space, carrying its secrets with it. And someday, perhaps millions of years from now, perhaps under a different sun, perhaps observed by beings we can't imagine, it might tell another part of its story. For now, though, its time with us is done. It came, we observed it, and it departed, leaving us with data and questions and wonder. That's perhaps the best gift an interstellar visitor can offer. Not answers, but mysteries that expand our sense of possibility and remind us how much we still have to learn. All those distant points of light in the night sky, each as a sun. Many have planets. Some of those planets might harbour life. A few might have civilizations looking back at us, seeing our sun as we see theirs, a faint star in a vast field of stars. And between all these suns, objects like 3I/ATLAS travel, silent wanderers connecting star system to star system across the ages. We're part of this vast cosmic web, this galaxy-spanning community of matter and energy and perhaps consciousness. Our lives are brief, but they're part of something eternal, the universe's ongoing exploration of its own nature. And in studying objects like 3I/ATLAS, in asking questions about what exists beyond our immediate experience, we participate in that exploration. We add our small piece to the growing understanding, our moment of observation to the eternal story of the cosmos. Sleep well tonight. Dream of distant comets and the spaces between stars. Dream of journeys that span millions of years and distances measured in light years. Dream of a universe vast and ancient and beautiful, and know that you're part of it, made of the same stardust, following the same physical laws, participating in the same cosmic unfolding. Good night.